So today we are going to be taking a look at the things that will prepare us for test number something. I forget what something. Maybe, I guess, test number 6 because this is study session 6. Maybe. It seems right. So what's on this test? Well, we have 5.3 and 5. Well, that's not a 5. 5.4. So 5.3 is the divergence test. Divergence test. And the integral test. Right? Divergence test and integral test. And then 5.4 is, let's see, 5.4, I'm trying to remember. Oh, yeah, the comparison test. So the direct comparison test. Direct comparison test. And the limit comparison test. So any of these tests could be on the test tomorrow. We don't know. So they said 5.3 and or 5.4. We will spend probably the most amount of time on the last two because they're also the ones that I have not practiced much at all. I don't think I've actually done any limit comparison test problems, and I have done a couple direct comparison test problems. But I have done all the problems for this, so hopefully that'll be faster to get through.
Would you say there's like something, like just guessing, of course we don't know, like would you say there's something that is more likely to be on the test? Like just guessing.
Limit comparison test. Most likely not divergence test. Integral test, I'd say yes, and most likely not direct comparison test.
So those two most likely, but not for sure.
If I were making the test, I would make these two the main focus. If I were making the test.
Okay, everyone needs those two on the test.
But I'm not the one making the test, so I don't know. But yeah, if I were making the test, I would say those two. They take the most amount of actual time to do and have the most thought that goes in mind. Divergence test is one limit. Direct comparison test, if you know what to compare it to, it's one step. It's one line. These two are more than that. Integral test and limit comparison test take some writing.
Yeah.
Right.
Yeah, because you have Horowitz, right? And you said you learn well from him, so that means you think like him. Mm-hmm. So if you think that, then probably he thinks that.
If that's what you think, then go with your gut there. Yeah, sure. I know I can't promise anything, but if that, yeah.
Oh, of course, I'm
sure,
kidding.
Sure, no, I know. Don't worry. I know. Okay, so let's start again. To anybody that just joined, my set of notes, which is right here for me, is in homework help. So you go to homework help, and it should be the first thing there. Let me just check that it is there. Yes, I did put it there. Good. So it's in homework help. You can go take a look and follow along with me. It has everything up to 5.4 and including 5.4. So yeah. Okay, well, let's take it one at a time. Let's start with the divergence test. Okay, so can I spell divergence? Divergence test. Sorry, I'm getting a notification. Yes. Divergence test is essentially this. Okay, so all these tests are if you're given some series, if you're given some series, and you need to be able to just decide whether it diverges or converges. Okay, and that's all you need. If that's all you need, then, which is most of the time for what we need in this course, we don't actually need to know what the series converges to. We just need to know if it diverges or converges. Then the next 4 tests and more tests in the later chapters are there to help us tell, just does it diverge or converge. To actually be able to evaluate what something converges to is sometimes almost impossible. So it's good to not waste your time, like if you were to try to find what something converges to not waste your time on something that diverges, so we can do these simple tests to figure it out. Okay, divergence test I think is the first one that I think makes some good intuitive sense. So I'm going to start it out not with the definition, but with actually just a drawing of it. So what it's saying is that, okay, so imagine we have a sequence here, right? We have a sequence that's like this. Okay, so it looks like that, and it goes up like this. Okay, so the series of this sequence, the infinite sum of this sequence, right? I can tell, I mean, assuming nothing fishy goes on after this, that it's going to diverge, right? Because every time, imagine the adding up all the sums is like adding up all the values of all these sequence points. Well, it just keeps getting more and more and more and more each time. So as you can see, the limit as n approaches infinity of this sequence is infinity, right? Again, I mean, we don't really know. Like it could just go back down to something else now, but let's just say we know that nothing else happens. It just keeps going up like that. So it would be infinity. So it's going to diverge because you keep adding more and more stuff to it. The infinite sum doesn't close in on a number. You just keep adding bigger and bigger numbers. Okay. Well, what about this situation? What if we have something like this? So we have da-da-da, da-da-da. So if we take this sequence that goes like this, and then it keeps getting smaller and smaller and smaller, and it goes to, well, it goes to 0, right? It approaches 0. This sequence, well, the series is going to add a big term, and then a smaller term, and a smaller term, and a smaller term, and a smaller. The terms always get smaller, right? So it looks like we're going to zone in on a number here. We don't know for sure, but it makes more sense for this. I think it makes more sense for this to converge than it does for this to converge. Because here we're adding bigger numbers each time. Here we're adding smaller numbers each time. So potentially it'll converge onto something. So essentially when the limit of an as when the limit as n goes to infinity of an equals 0, right? Then if it's 0, then it can possibly converge. Possibly converge. But if it's not 0, right? So as in we have a limit that's either infinity or just some other number, right? If it's not 0, then it definitely diverges because you're adding more and more and more each time to get to that number. So that's what the divergence test is. If the limit as n goes to infinity of an does not equal 0, then we know that the sum n equals 0 to infinity of an diverges. And that's the divergence test. Okay, so this is the definition of it. Definition.
Wait, if the limit equals 0 of the sequence, right? That means we still don't completely know?
Yeah, if it equals 0, we don't know anything. We don't know for sure.
Okay.
We didn't
But
learn
if
anything.
it doesn't equal 0, we know for a fact that it diverges.
Yes, if it doesn't equal 0, we know it
Okay.
diverges. Because there's just no chance.
Okay.
There's just no way that it could converge, right? There's just no way.
Yeah.
The only way it could converge is if this limit is 0.
Yeah, because like logically speaking, is it like if it's any number that's like not 0 and you keep adding it, you're going to eventually reach infinity?
Yeah, you're just going to keep adding that number, and that doesn't converge to anything. You're just going to keep adding that number, right? Maybe the limit is 1, so you just keep adding 1 infinite times. Well, infinity, right? So it diverges. So your limit has to be 0 to even have a chance of converging.
Okay. Makes sense.
And this is like 100% of the time. So like if it's not 0, then for sure
it diverges.
Thank you.
Yeah.
And this is the divergence test, correct?
This is the divergence. This is the definition of the divergence test. Yeah.
All right. Thank you very much.
Exactly. No problem. So let's take a look at just some example here. So I'll do. Well, I only actually have 3 examples from Horowitz, and they're all pretty short. So let's just do them, I guess. So the examples that I have are the sum. So evaluate, determine convergence and divergence or divergence for this sum, 5n minus 1. I always feel like writing a dx after because I feel like I'm doing integral. So, well, we have to determine if this converges or diverges. So the only thing we know how to do right now is the divergence test. So let's apply the divergence test. If that's an, then the limit as n goes to infinity of an is 3/5, okay, which is not equal to 0. Therefore, by the divergence test, sum n goes from 0 to infinity of an diverges. one thing to note quickly is that from the divergence test, you can never determine that something converges.
Wait, can you, I have a question.
Yes.
So like, that doesn't really make sense to me. I didn't really get that because like, isn't it either diverges or it converges? So like, if it does diverge, it doesn't that automatically make it divergent, or if it doesn't diverge, doesn't that automatically make it convergent?
Well, but this test doesn't tell you that something doesn't diverge. So it also can never tell you that something converges or that something, or that I should say a sum, but that something doesn't diverge. Right? This will only tell you that something diverges. The only time that you get a result from the divergence test is it saying something diverges. The only other option is that you got a 0 here, in which case it's inconclusive. You don't know that it converges. It's just inconclusive.
Adam, I'm derping out. Can you please explain how you got a 3/5?
3/5? Yes. So this...
I'm derping out.
In general, if you have a degree n and a degree n, you just take the coefficients in front of the highest power. But why?
Okay, sorry. Yeah.
But why is because, okay, if I want to take the limit as n goes to infinity of 3n plus 2 over 5n minus 1, to evaluate this limit, I'm going to multiply by 1 over n on the top and the bottom.
Okay.
1 over the highest power. This is going to become the limit as n goes to infinity of 3 plus 2 over n over 5 minus 1 over n. Take the limit as this goes to infinity. This term becomes 0. This term becomes 0. So we just left with 3/5.
All right. High school vibes.
Yes. Advanced functions vibes. That's what this is.
Yeah.
That's okay. That's okay. It's limits are very weird and confusing because we don't do it properly. So they're like, to me, they feel a little wonky.
Wait, can you like go after and re-explain that part? Because like it doesn't stay right with me. The whole never. Because like this is what I get.
Yes.
So the divergence test, in as far as I understand, it either tells you if something does diverge, or it gives you like we don't know anything. It's either does or doesn't. Like we don't know. Not it does or doesn't, but like it does or we don't know.
Yeah.
Correct.
Yes, correct.
But like, isn't the only thing that you can get converges or diverges? So like, if it doesn't diverge, doesn't that automatically make it converge? It's like, if we don't say no,
you can have a limit of 0. You can have a limit of 0 and still diverge. You can have
and one of them squared.
The harmonic series, right?
The harmonic series, exactly. You have a limit of 0, but you still diverge, right? So the divergence test, if you did the divergence test on this, you'd get inconclusive. That doesn't mean it converges, because this does diverge, right? This diverges. But the divergence test isn't going to give you an answer for it. The divergence test isn't going to be the thing that tells you it diverges. It's going to be some other test.
Yeah, one of it diverges. But like this just tells you yes for sure or don't know.
Yes for sure. It tells you yes for sure. The divergence test tells you yes for sure it diverges, or just period I don't know anything.
Sounds like thank you. Okay, that makes sense. But like, because they didn't sit right with me, because I thought like I guess a bit more like two-dimensional ways. Like it's either I thought in some senses like, if it's yes. If it's not yes, then it's no. You know what I mean? Kind of like with
I understand, but you gotta think about it a little differently. Yeah, exactly. So it's not yes, it's just I don't know.
Okay, thank you.
Right. Okay, our next one is determine convergence or divergence for this series 1 over n to the 4. So I can just take, if that's our an, 1 over n to the 4, we can just take the limit as n goes to infinity of 1 over n to the 4, which is 0. So inconclusive. Right? Let me just make sure that that's right. Yes, inconclusive. That's one word. Inconclusive. And that's all we can say right now. We don't know convergence or divergence for it. We will know in this chapter we will know, but it's okay. For now we don't know just by looking at this. We're not sure. Then the last example I have for divergence test is the sum n goes from 1 to infinity of 2 to the 1 over n squared, right? That's what it is? Yeah. So determine convergence or divergence for this series. If that's our an, we take the limit as n goes to infinity of 2 to the 1 over n squared. Limit as n goes to infinity is 1, right? Which tells us that this series diverges. Am I recording? Let me check.
Well, no.
Yes, I am. Diverges by the divergence test. Someone's got their mic on. Can everybody check their microphones?
It's Jeev something. Jeev.
Jivan, you got your microphone on. Okay.
My hand is like off. Can you unmute him or no?
I am not able to mute him. Everybody can mute him ourselves, but I am not able to server mute him. Oh, I think he's muted now. Okay, thank you. Very good. So that's all I have for divergence test. So is there any questions about the divergence test before we move on? See, again, it's very short. It's take one limit. So this is everything for the divergence test. Okay, otherwise I'm going to move on to the integral test. Okay, so the integral test is our next one, and I would say that this has a good chance I can't spell today. I'm a little tired, so sorry if I make weird mistakes. Integral test. I'd say this has a good chance of being on the test. Okay. So, so this one also, I'd say makes sense, not really visually, but I think it makes sense algebraically, right? So if we have a sequence defined by some function f, right? And we want to add up all the terms of an to infinity. Well, so let me actually see this for a second. Sorry. Converges. If it only has to converge. Yeah. Yeah. So we want to add up all the terms of this f of 1, f of 2, f of 3, f of 4, of all the actual numbers of it, right? Of all the integers of it. So that'll only converge if the broader thing also converges, which is the integral from b to infinity of f of x dx. If this converges, right, then this must converge, right? And it actually goes both ways in this case. If this converges, as in, so by this I mean the sum technically n equals b of an. So this goes both ways. If one of these converge, then the other one converges. So one way to check for this convergence is to check for this convergence. If this converges, then we know this converges. However, they do not converge always to the same number. We don't know that they converge to the same number. So you don't actually find a value for the convergence, but you do find just a decision of convergence or divergence. So that's the logic of it. If this broader thing, which is like a continuous adding up, we're adding up infinitely many x values, which is what the integral is. If this converges, then this must also converge, which is a less broad thing, right? And it works vice versa. So that's kind of the logic. But essentially, this is the integral test. I'll state it out kind of more formally, but that's the integral test. So in actual symbols, that's the integral from b to infinity of f of x dx converges if and only if the sum n equals b to infinity of an converges. And this if and only if means it works both ways. I'm pretty sure. Should be clear. I think that's what that means. Whenever I say something with such, so absolutely, I'm like, what if I get it wrong? So I'm pretty sure that's what that means. That's how we treat it, so it's okay.
Can you scroll down a bit because your webcam's blocking the end
Yes.
part of it?
Sorry.
All right.
There you go. So this.
And can you go to the top part real quick? Just a quick question.
Yeah. Into. Let me. Oh yeah. Okay. Sure. Yes. This part.
By that f of n, you mean only the points, right? Where they're just the integer values.
Yeah, because the sequence is defined by some function f of n. Right.
Okay.
Right. F of n.
Yeah.
Which is the function f of x, but only evaluated at integers, at positive integers.
At the integers. Okay.
Right.
Yeah.
Exactly. Okay, so this is what the integral test is, right? So let's try an example. To be clear, there is a criteria on it, which I realize I did not at all. Never mind. I was going to say I did not at all put on my note. I did put it on my note. I didn't forget that. The criteria is that f of x has to be continuous, positive, and decreasing. These three things have to be true. And then you can apply the integral test. The divergence test has no criteria, has no conditions or preconditions that you have to do. It works on any sequence. You can always do it, or series. But the integral test only works if your sequence is defined by a function that is continuous, positive, and decreasing. So let's try an example. This is an example from Horowitz's lectures. So I have the sum, determine convergence, divergence of this series. The sum n goes from 0 to infinity of e to the n. Sorry, 1 over e to the n, using the integral test. Okay, first we have to ask ourselves, is this continuous? Continuous. Yep, it's continuous. Is it positive? Yep, positive. And is it decreasing?
Yes.
Yes, it is decreasing. Because as n gets bigger, e to the n gets bigger, the denominator gets bigger, the value gets bigger. Value gets smaller, so we're decreasing. So we can apply the integral test. Because right now, if I were to take the limit as n goes to infinity, oh, actually, I would get 0. Oh, which would be inconclusive. So if I tried to apply the divergence test, you can see that I would be inconclusive right now. I'd get 0 as an answer. So the integral test will work here. Let's see. The integral test is saying that I'm going to check for convergence of this, the integral from 0 to infinity of e to the negative n, e to the negative x, sorry, dx. Note that this is the same. This equals an equals 1 over e to the n equals e to the negative n. So now we have to check for convergence of this this integral. So to do that, we say limit as t goes to infinity of the integral from 0 to t of e to the negative x dx. This is going to be negative e to the negative x evaluated from 0 to t, and I forgot the limit as t goes to infinity. Okay, now we evaluate. So again, I'll just say L for limit. This is going to be negative e to the negative t minus negative e to the negative 0. Okay, e to the 0 is 1, so plus 1, right? Then here we say limit as t goes to infinity of negative e to the negative t plus 1. Okay, well, let's rewrite this a little bit. This is going to be 1 minus 1 over e to the t, sorry. So the limit as t goes to infinity, this is going to be e to the infinity. 1 over e to the infinity is 1 over infinity. Sorry, I should be clear. E to the infinity is infinity. So 1 over infinity is 0. So it equals 1. This converges. Therefore, by the sum, the series converges by the integral test. I cannot spell integral test. Yes, we're good.
Wait, so I have a question.
Yeah.
So if it doesn't converge, is it inconclusive?
If it doesn't converge, then no. Then the other one diverges. I'm pretty sure.
So here it is kind of like, if not, then it
Yeah,
is.
I think maybe if someone else knows for sure, they could chime in. But I would say yes. Let me just see. Let's look it up maybe. If the if the integral test
Diverges.
diverges. Let's just see what it says. I can't spell. Let's just see what it says here quickly. Looking at that. Da-da-da. Or maybe the textbook would be here. Okay. Okay, so yeah, so there you go. If the integral is divergent, so is the sequence. If the integral is convergent, so is the sequence. So yes, it is a if or thing, or if, whatever. It's a you know, it matches always the result of the integral.
Okay, so here's another question.
Yeah.
So if you have the integral test, then why would you need the divergence test? Is it like just because this one covers everything, while the other one is like okay, yeah, thank you.
The function has to be continuous, positive, and decreasing. So it doesn't work at all if there's if it's a different kind of function. Right. So.
Okay. Thank you.
Right. No problem. Okay.
Sorry, can you scroll up a little bit to the row?
To the actual definition of it here.
Yeah. A bit up, sorry.
Yes.
Oh yeah.
Here.
Is it here?
Well, it's really this down here. It's this thing here. And and f of x has to be continuous, positive, decreasing.
Yeah, that's all. Thank you.
One thing I want to add, I realized, is that in 5.3, or is it 5.3? Yeah, in 5.3 we actually also have one other topic, which is approximating the value of a series, of a convergent series. So, approximations. Which I would say could quite possibly also be on the test, because that takes a good amount of writing. So, yeah, let's move on. Let's do a couple more integral test problems, and then we will just talk about p-series, and that will be everything. So let's start with okay, I have two examples. So let's do both the examples, I guess. So determine convergence or divergence for the following series: n equals 1 over n to the 4, right? So we couldn't do it up here. We tried it up in this question, 1 over n to the 4, and we got inconclusive by the divergence test. Let's try it with the integral test. So what I'm going to do is I'm going to take the integral from 1 to infinity of of x to the negative 4 dx. We're going to see if this converges or diverges. Well, first I should actually check. Does this, is this, what was the list I said? Continuous, positive, or and decreasing. So is this continuous? So let's see, is this continuous? Yes, it's continuous. It's not continuous at 0, but that's not in our range. We're going from 1 to infinity, so it's okay. Is it positive? Yep, positive. And is it decreasing? Yep, it's decreasing. The denominator only gets bigger, so the value only gets smaller. Okay. So from here, I can do the integral test. I know I can now. So let's take the integral. So this is going to, and I should say that this is the limit. Okay, I'll write it out fully. Limit as t goes to infinity of the integral from 1 to t of x to the negative 4 dx. So this is equal to the limit. Take the antiderivative, add 1 to the exponent, divide by the new exponent. So over negative 3. Add 1 to the exponent. Yeah. So I should write like that. Is that right? Subtract 1? Yeah, that is right. So we're taking this, evaluating it from 1 to t. So this is equal to the limit. It'll be negative 1 over 3t cubed plus 1 over 3 times 1 cubed. close that. We should open discussions. Discussions are open now. So this is, now we take the limit as t goes to infinity, right? That's our limit. So this is going to be, oh, is this the answer I meant to get? Yes, it is the answer I meant to get. Never mind. I saw the answer to a different question. And the limit is just a third. So therefore, by the integral test, the sum n goes from 1 to infinity of 1 over n to the 4 converges. And there's our answer. Okay. Anybody stop me if they have any questions?
Can you scrub a bit?
Yes.
Yeah, just this example. Well, this is still the same thing, just same example.
You want the last example?
No, I'm saying the one that you just wrote, that's just still integral test.
Yeah, it's still the integral test. Yeah.
Okay, thank you.
It's still the integral test. So I have one more example for the integral test. Any questions? Okay. I take that as we're good. So the last example I have for integral test, and if you want more examples, just tell me the textbook questions and I will do them, is the integral from 0, determine convergence or divergence for, I can't find it, there we go. The sum, n goes from 0 to infinity of 1, what does that say? This 1 over the square root of 2n plus 3. Okay. So now if I were to take the limit, if I were to do the divergence test on this, take the limit as n goes to infinity, I would get 1 over infinity, which is 0. Divergence test is inconclusive. So now we have to ask, can I do the integral test? Is this continuous? Okay,
Yes.
well, let's make sure. Let's just make absolutely sure. It would be discontinuous when the denominator is equal to 0. So when is 2n plus 3 equal to 0? Well, when n equals negative 3/2, but we're going from 0 to infinity. So we don't have to worry about it. It is continuous. What is it positive? Yep. There's no subtraction or anything happening. It is positive. Very good. And is it decreasing?
Yes.
Yeah, it is decreasing. Right? So we can do the integral test. What that means, I'm going to take the integral from 0 to infinity of 1 over the square root of 2n plus 3. 2x plus 3 dx. This is just a u sub, so I can just say u equals 2x plus 3, du equals 2 dx. Right? Hold on. Did I do that right? Yeah, I did. Okay. Then I will just say this is equal to 1/2 integral 0 to infinity of 1 over the square root of u, which I'm going to write as u to the negative 1/2. Okay. Du. This is going to be 1/2 integral 0 to infinity. I realize now I'm not doing the limit, which I should, but it's okay. And actually, I will just evaluate it now. So add 1 to the exponent and u to the 1/2 divide by the new exponent. So u to the 1/2 over 1/2. Right? Yeah. And evaluate that from 0 to infinity. So this is going to be 1/2. Okay. Infinity. Okay, I can't do that. Let me do the limit.
Wait, can't you simplify?
What'd you say? Sorry.
Can't you simplify? Since it's a half and half, can't you cut them out?
This half and this half?
The other one in front, right in front.
Oh yeah. Yes, I can do that. Yep. I guess I will do that actually. Yeah, that makes sense. So this is just n root n essentially, evaluated from infinity 0 to infinity. Okay, so what do we get here? Well, evaluated at infinity, we get the square root of infinity is infinity. Minus 0 is infinity. Whoops, is infinity. Wow, I cannot draw an infinity sign. There you go. Therefore, by the integral test series is divergent.
And
yeah.
And one more thing, you have one exact same answer with the divergence test. It would have worked here too, wouldn't it? Because it just like approaches zero. Oh wait, no, it wouldn't.
It would approach. Yeah, no, we'd get the limit of 0, which means we would get inconclusive.
Interesting.
We'd get inconclusive with the divergence test.
Okay, thank you.
Right, no problem. Okay, a last thing to talk about quickly is a p-series. So there's a nice, Horowitz went through a nice showing why it's true, which maybe I can do at the end if people want me to see it, but it's not really worth the time that much. It's just a rule to memorize. So the sum n goes from 0. Does it have to be 0? It doesn't have to be 0. I'll start it at 1, but I think it doesn't have to be 0. It has to be greater than 0, actually. Sum n goes from 1, let's just say 1 to infinity, of 1 over n to the p. So p is just some power. This is called a p-series. Okay, this is what a p-series is. And it converges if n is greater than or equal to 2. Sorry, p is greater than or equal to 2. Right? Which can also be written as greater than 1. But I don't know, for some reason I just like saying that, because including 2. We can do 2 and up, it converges. Otherwise, it diverges. So 1 over n squared converges. 1 over n to the 200 converges. 1 over n diverges. And you can show that it's true by the integral test. But again, if people want me to show that, I'll show that at the end. It's not exactly worth the time. It's mostly, yes.
Isn't it greater than 1? Like, because I feel like between 1 and 2, like, fractions can also work.
I guess you're right. I guess it can work for fractions. You're right. Yeah, you're right. Greater than 1. Yes, because if you have a power of 1.5, that still counts as a p-series. That converges. Yep, you're right.
Yeah.
So it converges if it's greater than 1. Otherwise, if it diverges. So again, if p equals 1, it diverges. This is going to be very useful in the next chapter, because we can immediately tell that 1 over n to the 5, converges. Sum as that goes to infinity. Okay, let's now talk about approximating areas. So I'm in Calc 1 still. Let's talk about approximating series, which is very similar to approximating areas. I'm not surprised I made the mistake, but is different. So we're looking at approximations of convergent series. So, like I said before, if you have just some random series, before I actually get going on this, any more questions about integral test? Any last questions here? We can, of course, go back to it anytime. Okay. So, approximations of convergent series. Like I said before, if you have a random series that you know is convergent and you want to figure out what it converges to, sometimes it can be impossible, almost impossible, to find what it converges to. However, we can create approximations for any series using the integral test, and this will get us within any degree of accuracy we want to the actual value of convergence. Okay, so to do that, let's just say I'm going to do it in general, and it makes the most sense to me in general. So let's see if we can do it. If we have some series, infinite series, sum goes from n equals 0 to infinity of an. We know it's convergent. First of all, we know this is convergent. We know this is convergent. Okay, how do we get an idea of what this converges to? Let's say this equals s. Okay, it equals s here. The infinite sum is equal to some finite value, because since we know it's convergent, we know that there is a finite value, but we don't know what it is, so let's just say it's s. We can always approximate it by taking the kth partial sum, right? We can approximate it by taking the kth partial sum. Or I guess I call it the nth partial sum here. No, I call it the kth partial sum here. So I'm going to stick to what I know some professors, my professor definitely called it the nth partial sum, but that confused me. So I'm going to call it by k's, everything by k's. So the kth partial sum is approximately the value, right? If we add up the first 5 terms, it's not very accurate. If you add up the first 5 million terms, it's more accurate, and more accurate as you go to infinity, right? But, well, it's exactly accurate as you go to infinity, but we don't know exactly how accurate it is. So we want to have some sort of gauge. We want to measure how accurate this approximation is. Approximation is. So how do we do that? Well, you can kind of think of this infinite sum, this finite value, as sk plus something. There's something we're missing. There's a little bit that we're missing there, right? Because if I take the 5th partial sum, then there's infinitely many partial sums I'm missing, right? But there's a bit that I'm missing there, and we don't know how big that bit is. So if I just say in general, remember this is the actual value that it converges to. Sk is our approximation, the kth partial sum. There's a little extra bit there that we're missing, right? I'm going to call that the remainder, rk, r sub k, right? And by asking this question, how accurate is this approximation? Equivalently, we can ask, how big is rk? That's an equivalent question. How accurate is this? How far from the answer are you? Is like, how big is this remainder? How big is this difference from the answer? So now we need to figure out a way to bound what rk is. Okay, what's rk is between these two values, between 0.0001 and 0.0009 or something, right? So how do we do that? Well, the main part of approximating series is this idea right here, is that the sum, the infinite sum, is bounded between these two things, not equals to, bounded between these two things. The partial sums, plus the remainder, right? The remainder. We can guess what the remainder is using an integral. Okay, so I'm gonna write it out now, and I'll explain right after. F of x dx, integral from k to infinity of f of x dx. So notice down here is k plus 1, and down here is k. To explain why this is the remainder, first of all, this is a underestimate, or no, s is bigger than, this is an underestimate, and this is an overestimate. Right? This is an overestimate. To understand why this is happening, though, why is that an underestimate? Why is that an overestimate? Let me look at my notes here, and this image might help. So I'll just take a screenshot of it and put it in my notes here. So someone's got their microphone on.
Ask it.
Someone has their microphone on. My guy. Dog.
Say it, but I didn't want to.
He's gone. Okay, good. That's fine. Okay, so to get an idea of why this bounds the infinite series, so the infinite sum, is the area under the curve, essentially, right? It's these chunks, like this, And so this integral right here is the underestimate, right? Because we take the integral from k plus 1, or here it's called n plus 1, but imagine it's just all k's. So k plus 1 to infinity, right? That's this underestimate that's happening here. So we take the partial sum that we know. Imagine the partial sum we know is up to here, right? That this is sk, right? I should be clear. This is sk. And this is sk. So the actual value of this integral, of this infinite sum, is somewhere between this underestimate, because look, we have these little gaps in here. So it's under the actual value, and this overestimate. So that's what this is saying. The actual value of the infinite sum is bounded between the partial sum that we know the value of, plus this underestimate, and this partial sum that we know the value of, plus this overestimate. So from this, I'm going to copy this actually. From this, we can bound the remainder. And we do that by this. On all three parts of the inequality, we subtract sk. Okay, so to subtract sk, we have, and OneNote is doing the thing again. So we subtract sk from all the parts of the inequality. So this is the integral, the integral from k plus 1 to infinity of f of, f of x dx, s minus sk, integral k to infinity of f of x dx. And now s minus sk, remember what I said before, s equals sk plus rk. So s minus sk equals rk. So we know for a fact that the remainder, rk, is bounded between the integral of k plus 1 to infinity of f of x dx and k to infinity of f of x dx. So what this means is that if I have some sequence an, and I take the series, the infinite sum, as n goes from 0 to infinity, 0 to infinity of an, I decide to approximate this with sk. The remainder, how accurate this is. Remember, the equivalent question we're asking, how accurate is this? Equivalently, we can ask, how big is rk? Well, rk is between those two values. Integral from whatever partial sum we stopped at, plus 1 to infinity, the integral of that from f of x, the integral of, from those bounds of f of x dx, and the partial sum we stopped at to infinity, those are the bounds of f of x dx, that's the upper limit. And that is what bounds rk. And this is exactly how you estimate remainders. Or I should say estimate accuracy of partial sums. Okay, any questions? Did that make sense? Sorry. Okay.
Wait.
Yeah.
You subtracted everything. SK is the same as. Oh, hold on. Because S is equal to SK plus RK, you switched out in the middle there just to be RK, right?
That's right. That's right.
And then that's just equal to the lower bound, upper bound basically are underestimate and overestimate.
Yeah, they're bounded. They bound what the remainder could be.
Yeah, so. And then what exactly are we solving for though?
The remainder. We're trying to see. We're trying to bound the remainder. And usually, all you actually need is this upper bound. All you actually need is that. You only ever want to know how inaccurate could it be. You don't really care that much about this because it's in the range. So usually the question will say, it'll say put an upper bound. So you just care about this upper bound, right? What is the maximum inaccuracy that you could have,
It'd be okay. Makes sense.
right? So it cuts out half the calculation. Okay, so I hope that made sense. Let's try some questions. I essentially only have one question that, well, two really that use this. So there's only one that I have that actually like straightforward uses this. So, for the sequence, for this infinite sum, which is a series, not a sequence, for the series, n goes from 1 to infinity of 1 over n to the 4. Determine or approximate s. This is equal to s. Approximate s. Write that differently. Approximate s using S5. And determine R5. Or I guess I could say determine the bounds of R5. How accurate is this? So if I estimate with just 5 partial sums, how accurate is this? Okay, well, first of all, you have to find what S5 is. You have to manually calculate that. We don't have a formula for the partial sums for this, so we just have to manually calculate it. So S5 equals A1 plus A2 plus A3 plus A4, plus A4 plus A5. So put 1 in there, it's 1. Put 2 in there, it's 2 to the power 4. I'll just say 1 over 2 to the power 4. Plus 1 over 3 to the power 4. Plus 1 over 4 to the power 4. Plus 1 over 5 to the power 4. This is right. So, well, I will just tell you that this is equal to... according to the professor here, 1400131 over 1296000. I'm gonna make sure because I kind of copied it sloppily, so I'm actually gonna do it quickly. 1 plus it'll take me 1 second. 1 over 2 to the 4 plus 1 over 3 to the 4 plus 1 over 4 to the 4 plus 1 over 5 to the 4. I got... Oh, it doesn't tell me as a fraction. So I'm going to have to... Oh, I can just compare it to this fraction. This fraction is 1400131 over 129... Oh, boy. 12961. 12961212. Yep, okay, we're good. That is the answer. So that is what that adds up to. Okay. Okay, we know this now. Let's bound... let's bound what... Hold on. Oh, okay. Yeah. Sorry. First, what we're going to have to do is, well, we don't have to do it in this order, but the easiest thing to do first is to bound the R, the remainder, to put bounds on the remainder. Because you have to calculate these integrals. If you want to put bounds, if you want to estimate S, you have to anyways calculate these integrals. So let's first find bounds on what the remainder could be. So once again, the remainder is going to be the integral from 6 to infinity of 1 over x to the 4 dx. Sorry, the remainder is going to be between this, R5. The integral from 5 to infinity of 1 over x to the 4 dx. Okay, so this is going to be, well, what is this integral? It's going to be, add 1 to the exponent, so it's going to be negative 3, x to the I did it just on the other page, didn't I? X to the negative 3 divided by the new exponent. And evaluate this from 6 to infinity, R5 is going to be x to the negative 3 over negative 3, evaluated from 5 to infinity. So, evaluate this at infinity. That's just, ooh, that's not good. Oh, never mind. It is good. I was going to say problem. No problem. It's going to be negative 1 over 3x cubed, evaluated from 6 to infinity. Just going to write it nicer. R5, minus 1 over 3x cubed, evaluated from 5 to infinity. So evaluated at infinity, that's just 0, right? Evaluate at 6, minus it, evaluated at 6. This is going to be, well, whatever 1 over 3 times 6 to the power of 3 is, R5. And this is similarly going to be 1 over 3 times 5 to the power of 3. And there we go. We know our remainder, the remaining amount we have in the sequence, is at the most only, so this value here is 0.00266 repeating, so 26 repeating. That's at the most how inaccurate it is. It's that far away from the answer. To be clear, our estimation, this right here, is at the most 0.0026 repeating away from the answer. To be clear, the answer is the exact value of what this series converges to. Okay, and now let's put bounds. Let's put bounds on our S. Approximate S. What is S going to be? So S is going to be between this integral, the integral we evaluated, 1 over, so I'll write it out fully. S5 plus the integral from 6 to infinity of 1 over x to the 4 dx, S5 plus the integral from 5 to infinity of 1 over x to the 4 dx. Well, luckily we already know those integral values. So S5, and we also know S5. So I have it on my sheet here. So S, the exact value, is somewhere between 1400131 over 1296000 plus 1 over 3 to the 6 cubed and this plus 1 over 3 to the 5 cubed. Sorry, 1 over 3 times 5 cubed. I think I said it wrong here, but hopefully you're also watching as I'm talking. And so now we know bounds. We know S is somewhere between these two values, right? And we just do this by using our remainder, right? So it's essentially this is the amount we know. We know it's up to here. And then it's either this far, the remainder is either this much or this much. This is the lower bound on the remainder, this is the upper bound on the remainder. So the S is somewhere between what we know plus each estimate. And there we go. That's the answer. Technically, the answer is this box and this box. You could add those together, but it doesn't matter.
Wait, the first box that you just made, was it with the R value?
That's the R, yeah. So the question was approximate S using S5, that's the final box, and determine R5, and determine the bounds of R5. So these are the bounds of R5.
Yeah.
And we approximated S.
It's in the bounds of R5 on both ends again, right?
What'd you say? Sorry, what was it?
The underestimate and overestimate is the same thing as the bounds for R5 or the R in general.
Well,
RK.
it's not exactly the same thing because there's this SK here.
Yeah,
right? There's
there's
SK.
the S.
Yeah, but yeah, this comes from here, and this comes from there. They match up like that.
Okay.
Right. Exactly. Okay, so how does everybody feel about approximating the value of a sequence. Yeah, this could also be on the test tomorrow. I'm going to be honest. It could be. I don't know, but. Okay, and essentially, this is the end of 5.3. This is the end of 5.3. It took us an hour to get through the content. This is the end of 5.3. So, how does everybody feel about 5.3?
Pretty easy so far.
This is everything in 5.3. Yeah.
Honestly, it's just the approximation with the s equal sk plus k. I remember like there being like questions like how many terms would you have to do to get
Within a certain accuracy?
within a certain accuracy.
Mm-hmm.
Yeah.
Do you want to do
That's
one of
the
those?
other thing. Yeah.
Sure. I have one here. He did do one. So let's try it.
Cool.
So using the sequence and the series from the last example, so another example, but using the same sequence, or series, I keep saying the wrong one, n equals 0 to infinity, or n equals 1 to infinity. Should have been 1. It was 1. 1 over n to the 4. Find the smallest n where Rn is less than or equal to 1 over 1/10,000. So we want to be within 1/10,000th of the answer. So to do this, what we're saying is we want that Rn is less than or equal to, okay, 1 over 10,000, right? Okay, I already said that. What do we know? we want this. What do we know? We know that Rn is less than the integral from k to infinity of 1 over x to the 4 dx. It's just that in this case, I guess I should be clear. It's worded with an n, but I really mean k here. I'm just switching the question because the letter is different, but that's all it is. I'm just changing the letter. Because I've just been using k the whole time because I think it makes more sense to me as k, because when I say n's, I'm thinking of terms in a sequence. So k to me is the partial sum. So the kth partial sum, what is the remainder of that? So hopefully that also makes sense to you. Just switch the letters. That's all I did there. So now let's find the smallest k where rk is less than or equal to that. So if rk is less than or equal to this, we want this to be less than or equal to 1 over 10,000. We want this inequality to be true now. Right? So I do that. I just do it. Well, what is this? Right? What is this value? Well, I get, it was negative 1 over 3x cubed evaluated from k to infinity, less than or equal to 1 over 10,000. Well, what do I get out of this? I get 1 over 3k cubed, less than or equal to 1 over 10,000. Right? And I just solve for k. And I'll just tell you, well, I mean, okay, we'll do it still. So 3k cubed greater than or equal to 10,000. And then k cubed greater than or equal to 10,000 over 3 in a cube root. Sorry, k is like that. Right.
Yo, did we?
Yep.
Did we use even though it's 1 to infinity, right? We because it's asking for the smallest term, we technically use infinity as the upper bound that they already gave us, right?
But we're just looking for the remainder. We just want the remainder to be a certain amount, right? So, oh yeah. We just want the remainder to be a certain amount. All right, I thought we made a mistake for a second, but we did not.
Go down.
What'd you say? Sorry. Go scroll down.
For a
Scroll
bit.
down. Yeah.
Yeah. So see right here, you have between k and infinity, right?
Oh, here.
from k to infinity.
Yeah.
And then we just, I don't get how you just let it equal to, we ignored the,
Oh no, just evaluate this. Just evaluate. You'll see. Just evaluate. It's gonna be negative 1/3 times infinity cubed plus 1/3 cubed. This goes to 0, so it's just 1/3 cubed.
okay, what happened to the negative though?
Because it's minus. It's minus 1/3 x
Yeah.
k cubed.
Makes sense.
So that goes like that.
Yeah.
And that goes there.
Right.
Yeah. And so this has to be greater than 14.938 ... So in other words, k has to be greater than or equal to 15.
Is that 15? Oh, 14.
And that's the answer. K has to be greater than or equal to 15. So we have to take 15 partial sums to be within 1/10,000th of the answer. Okay, so I do have 2 more questions from this. One's an integral test. I guess we could do... The integral test one is... The difficulty of the integral test is doing the integral, but this is a simple integral. So it's okay. And
Wait, are you saying that?
Yeah.
You were saying that the difficulty in that question is not the concept, but just the type of integral.
Just doing the integral, but no, but the concept is fine. It's just when to apply the integral test, and then doing the integral. It's not a difficult integral to do. It's a u sub, 1 u sub. So I think we're good with 5.3 then, unless there's any more questions. Please let me know. Okay. Then I will move on to...
I feel like it's just like so straightforward. I feel like it's like in the questions themselves that you'll find difficulty.
Difficulty,
like
yeah.
And not the concept,
We'll see. We'll see how it goes. Yeah, I don't know. Does anybody want to take a break? I'm okay not taking a break, honestly. I'm okay. I guess I should respond to one text. But
We have a quick question.
yeah.
Can you scroll up a bit?
Yes, I can.
I thought when you when you flip the equality sign.
Oh, here, this sign, yeah.
Don't you flip that when you multiply by one side by a -1 or a negative? Thing?
Yeah, that's true. And also when you flip a fraction.
Okay.
When you flip both sides. You flip both sides of the fraction, and it'll swap the inequality. Yeah.
Okay, got it.
You guys give me just 1 second. Okay. Sorry about that. I guess I should say one more thing. Okay, so let's carry on now into 5.4. So 5.4 are the comparison tests. Right? Comparison tests. So the comparison tests are 2 different tests that we use to, again, determine convergence or divergence of some series. So the first one we do is called the direct comparison test. So that's what we're going to start with here. Direct comparison test. This is very, very similar to the comparison test that we had, or comparison theorem that we had in 3.7 with integrals. So what this is saying is that if I have two sequences, one green, one red, right? One is notably bigger than the other for all n. Let's maybe say, I have this going down like that. That's a sequence. And then I have another sequence that's smaller for all n. Okay. If the green one converges, then the red one converges. If the red one diverges, then the green one diverges. The opposite statement is not true. So essentially what this is saying is that imagine the red sequence. If the red sequence doesn't converge onto a number, as in this amount under the curve grows to infinity, then without a doubt, this area under the curve will grow to infinity because it's bigger than this pink area. The purple area is bigger than the pink area. So if the pink area diverges to infinity, then the purple area will also diverge to infinity. Okay, so that's what this is saying. If the red one diverges, the green one also diverges. Okay, but now what about this other one? If this green one converges, which I'll do, I'll probably do it with the right colors. So if the green one converges, as in this area has a finite value, then the area under the red curve will also have a finite value because it's less than this bigger one, which has a finite value. So it must converge because it's kind of getting squeezed in, right? This is identical to the comparison test from 3.7 for integrals. So similar that I'm basically showing it with an integral. So we will use this. What you have to do is you're usually given the red one. You're usually given the red curve here. The red sequence. So you see it's not a curve, it's a sequence. And you have to choose some green sequence that's always bigger than it and determine if it converges. If it does converge, then you know that the red one converges. If that bigger one diverges, you didn't learn anything about the red sequence. What you then have to do is find another sequence that's always smaller than it, always smaller than this red one. Determine if that diverges. If that diverges, then the red one also diverges. If that one converges, you learn nothing again. And you need to use a different test. So let's do it with an example. And actually, before I do it with an example, let me actually write out, instead of colors, let me write out the actual comparison test.
Yes, please.
So the actual...
Did you use red to indicate a smaller...
The red one is the smaller one, yeah. The red one is the smaller one. The green one is the bigger one. And maybe I'll make those more pronounced. Right. And they go to infinity.
I have a question.
Yeah.
Isn't that the opposite of what the P-series test said? The P-series was like, if it's greater than 2, sorry, if it's greater than 1, then we have something that converges.
Uh-huh.
Right? Wait, no, sorry, I'm getting my graph stuff mixed up. So if it's a larger exponent in the denominator, that means it decreases faster. So that means it have a... Okay, yeah.
It would be the lower one. It would be the lower one.
Lower one, okay.
Right.
Because as a bigger number, I was thinking it was the bigger one.
Yeah, I understand.
Yeah.
So if an is greater than 0, first of all, positive and stuck between bn and 0, right? For all n greater than or equal to n naught. And essentially what this means is that after some point, it doesn't have to be right at the start, that it's always greater than the other one. But after some point at least, so n naught could be like 1. After 1, then this is true. Or it could be 10, whatever. After some point, we're going to infinity anyway, so it doesn't matter. So for all n greater than n naught, then if the sum as n equals 0 to infinity of Bn converges, then the sum n to infinity, or I should say n equals 0 to infinity of An also converges. Again, to note, the opposite is not true. If An converges, you don't know anything about Bn. And if the sum n equals 0 to infinity of An diverges, then the sum, whoop, that's not a sum sign, n equals 0 to infinity of Bn also diverges. And there we go. That's the comparison test. So in a sense, we have to pick a Bn to compare it to. And go from there. So let's try one then. Let's try an example. So the hardest part of this is choosing what Bn you're going to use, right? So just to be clear, we've entered territory that I have not done much practice on. So I think it's good to start with the Horowitz questions and then go into some textbook questions that I haven't done yet, or we'll just see what we go to from there. So this, let me see for a second here. What's the, yeah, okay. So let's start with this example. Example, the sum n equals 1 to infinity of 1 over 5n cubed plus 2n squared plus 3n plus 1. Okay. So determine convergence, divergence of this series. That's the question. So we have a sequence, an, 1 over 5n cubed plus 2n squared plus 3n plus 1. Let's find something that's always bigger than it, right? What's something that's always, always bigger than it, and is positive. They're both positive. So this is already positive, right? This is a positive number. We have to find it's also positive, so we know that's not a big deal. So we're just looking for something that's bigger than it. Well, what do we know right off the bat? Okay, we know n cubed equals n cubed. So, okay, I'm going to show 2 ways to do this. Right, what I would choose for Bn is 1 over n cubed, because we have a degree of 3 on the bottom. This is always bigger because this denominator is bigger, right? But I think it's a good strategy to be able to like show this with an inequality somehow. So it's not very hard to do. We know n cubed equals n cubed, right? We know 5n cubed is greater than n cubed. And we know that 5n cubed plus 2n squared plus 3n plus 1 is greater than n cubed. Whoops, that's not true. Yeah, it is greater than n cubed, sorry. That is true. And now when we take the reciprocal, plus 2n squared plus 3n plus 1 is less than 1 over n cubed. And now we have something that actually shows why we're choosing Bn. Why we're choosing that specific choice for Bn. Right? Which is because that inequality is true. Okay, so now that we have a choice for Bn, we compare them. What we want to see is that if this converges, if Bn converges, then An will also converge, because this is the bigger one, right? So if the bigger one converges, then the smaller one will also converge. The smaller one will also converge. So let's try, well, do we know that Bn converges? Bn converges, right? Bn converges. Because it's a p-series. Okay, so therefore, An converges by the comparison test. Oops. So you see how comparison test is also kind of like a one-line thing. You just sort of write it, and then you do it. There's not much calculation. Usually, you choose a sequence to compare it to that is very, very quickly identifiable as convergent, such as either a p-series, a geometric series, or, if I can think of another one, I can't really think of another one. P-series, geometric series. Yeah, can't really think of another one. So those are the two that I would choose, either a p-series or a geometric series. And either one would be something that you can quickly identify as convergent, right? Because remember, geometric series is convergent for absolute value of r less than 1. And p-series is convergent for p greater than 1. So, yeah, and there we go. That's that question done. Any questions about that question before I move on to the next one?
Yeah, so you mentioned that like they both need to be positive or something?
Yeah.
Like just so is that just like do they both need to be of the same sign or
No, they both need to be positive.
okay. So AN will probably never be positive.
Well, AN is positive here.
Right. Because you're saying that like if AN is positive then BN should be positive like as a result.
Yeah.
But there's not like an opposite, like if AN is negative.
Choose BN that's negative. I think you actually are allowed to do that. I think I remember Horowitz saying that. I don't have it in my notes though. Let's see if I can find it. I think you are allowed to do that and just turn them both positive.
Okay.
Maybe I'll look it up, because then I think the result convergent divergent will still be true. Can you do direct comparison test with two negative series? Let's see. Negative. Is this the comparison test? It's the only time he says negative. No, it's not here.
That probably just means that like we won't get negative, like a negative AN.
We probably won't get a negative AN, but
Yeah.
I mean, I'm not 100% certain, but I think you are allowed to do it. If you get AN, choose another BN that is always smaller than it, right?
Oh yeah.
And then make them both negative. Well, multiply them both by -1, so make them both positive. And then you can just apply the normal
sign would
test.
change. Yeah.
Sign would change, and then you can actually apply the test, and your result would be the same.
Okay. Yeah. Thanks.
Wait, you said make AN smaller. If AN was originally larger than BN, you're saying you'd multiply by a negative?
No. If AN was negative, if AN was always a negative sequence, right? It was just always negative. Then you could choose a BN that's always smaller than it, more negative, and
So it.
Mhm.
Oh no, because it's right now it's AN greater than or equal to 0, less than or equal to BN. So you'd shift it around because it'd be the other way. So you'd have like these signs would have been flipped. So to just add a negative would flip back the signs.
I guess so. Yeah.
Oh, okay.
You'd flip it, or you'd
Okay.
flip.
If they were negative, it would have been
you'd
the
actually
other way
you
around.
just flip the position of 0 and BN. Yeah.
And then.
But then you'd make them. I don't actually know if this if this works.
Yeah, I've never seen it though in my class.
I did hear. I remember Horowitz saying something like that, and I wish I could remember, but I can't remember now. And seems like I didn't write it. So he did say something like that. Maybe I'll try to find it out. I'll try to look it up. Maybe I'll look in the chat here too. Yeah. But for the most part, you're going to deal with a positive AN, and you choose a positive BN that's bigger than it always to compare it to. Okay, are we good to move on to this question here? Okay, I think we are. So here we have the series n goes from 0 to infinity of 1 over 3 to the n plus 2. So our AN sequence is 1 over 3 to the n plus 2. Bn is something I have to choose. So first of all, this is always positive. Good. Is there a Bn that's always greater than it? Well, I can right away tell you it's going to be 1 over 3 to the n. But again, let's do it with an inequality. Well, I know 3 to the n is equal to 3 to the n. I know 3 to the n plus 2 is greater than 3 to the n. And I know 1 over 3 to the n plus 2 is smaller than 1 over 3 to the n. So this is my an, always smaller than my bn. So this is my an, this is my bn. Okay, so now we have something to compare it to. Now, first of all, does bn converge? Does bn converge? Right? Well, it does, yep, because it is a geometric series with an r value of 1/3, right? Which is the absolute value of 1/3 is less than 1. So what that means is that an also converges. So therefore, by the direct comparison test, the sum n equals 0 to infinity of an converges. And there we go. That's the question.
You said absolute value of r, but if it converges, wasn't it like r equal, right, between -1 and 1?
That's the same
Or
thing.
is that something else?
That's the same thing.
Okay. Yeah.
Is completely equivalent
Yeah.
to absolute value of r less than 1.
Yes.
That means the same thing.
Okay.
That means the same thing. So yeah. Okay, so there's that question. I have one more practice before we go to limit comparison tests. So let's take a look. For this one is going to be find convergence divergence for the series n equals 2 to infinity of 1 over ln n. That's it. So we have to determine a is that all it is? Ln n? Yeah. Yeah. We have to determine a bn for our an. So an is 1 over ln n, right? We have to determine something that's always bigger than ln n. Okay, so what's always bigger than ln n? Well, what's always bigger than 1 over ln n? Well, we know that, okay, first of all, n equals n. Ln n is smaller than n. Okay, ln n is smaller than n. We take the ln of something, it's going to get smaller. Yeah. Well, so from here I can say 1 over ln n is greater than 1 over n. Okay, hold on. We ran into a problem. Not a problem. It's okay. Like we'll get the right answer. So let me write something here. There's two ways you can use the comparison test. So if you have an, you can either choose a bn that's always bigger and show that it converges, because then that will apply to the an. Or you can choose a cn, I'll call it a cn, which is always smaller than an, and show that this diverges, because that will also apply to an. So what you choose to do really depends on, do you think this converges or diverges? So 1 over ln n, I don't know if it converges or diverges. I don't really know how I would figure that out on my own. But probably I would try to find a bn that's greater than it and have no luck. So then I would say, okay, what if I try to find a cn that's smaller than it? And that's exactly what I did here. Cn equals 1 over n. Cn is always smaller than an. We know that Cn diverges. It's the harmonic series. Right? And by that, so by the direct comparison test, the sum n equals 2 to infinity of 1 over ln n diverges. Whoops. There. And there we go. So I will highlight this. These are the two ways to use the direct comparison test. Just like this. Okay, any questions about what I just did right there? No, I think we're good. Okay. Then I will move on to the limit comparison test, which I have done no practice of. So we're technically on the last thing. So go back to our start. Let's go back to the start here. We did divergence test, integral test, approximations. We did the direct comparison test, and now we're just on the last thing, limit comparison test. So the limit comparison test is this. I don't really have a very intuitive understanding of why it works, so we're just gonna have to go with what it says. Essentially, you take any two series, AN, BN, which are both positive. Any two series that are positive. Okay, so you take that, and then you compute the limit as n goes to infinity of AN over BN. There is no criteria of what AN doesn't have to be bigger than BN, or BN doesn't have to be bigger than AN. They just have to both be positive. You compute their limit. Okay. If the limit, there's three possibilities that could happen. So first possibility, the limit as n goes to infinity of AN over BN is between 0 and infinity. It's a positive real number. If that's true, then if AN converges, BN converges. If AN diverges, BN diverges. I guess a better way of saying this is, if this is true, they both either converge or diverge, but the same. So if AN converges, BN converges. So it's whichever one you know. So if you do this and you get a number between 0 and 1, and you know one of them converge, then the other one converges. Or you know one of them diverge, then the other one diverges.
Well, what do you mean by AN and BN are greater than 0? Like, they're positive?
They're both positive.
They're positive?
They're both positive. Yeah.
Okay, so that's all.
Yep. This just means both positive. Okay. The second thing that could happen is that you get the limit as n goes to infinity of AN over BN equaling 0. Okay. If this happens, then if this happens and BN converges, I should be clear. When I say BN like this, when I say BN converges, I really mean the sum n equals 0 to infinity of BN, right? But I just keep it simple. I just say BN. So, but just so I'm not confusing anybody, that's what I mean. It's just that it's a lot of sums to write, so I just say BN. So if then BN the sum n goes from 0 to infinity of BN converges, then what? Then AN also converges. And the last thing that could happen, so if you get 0 and BN diverges, you learn nothing. So if limit as n goes to infinity of an over bn. So the third thing that could happen is that you get infinity as the limit. If this happens and bn diverges, right, and bn diverges, then an also diverges. And that's the limit comparison test. We have two positive sequences. You calculate this limit. Okay. If that limit is a positive real number between 0 and infinity, they either both converge or both diverge. So you got to figure out one of them, if they converge or diverge. But then once you know that, you know the other one. If you get 0 and bn converges, then an also converges. And if you get infinity and bn diverges, then you also know that an diverges. Any other situation is inconclusive, such as if you get a negative number. Inconclusive. You won't get a negative number, but whoops. I just closed OneNote by accident, I think. You won't get a negative number, but somehow if that happened, you will be inconclusive. Okay, so let me just see where I'm at. Okay, so I do have 3 pages of practice problems for this. So I think we can give it a try. Any questions about this definition for the limit comparison test?
I just have one question though.
Yeah.
For the an over bn with the between 0 and infinity, you'd still have to like at least know one of them, right? So like if but for this case, if either an or bn is, let's say, just, I know that this wouldn't work, but let's say 1 over n squared was divided by something else, which is bn, and we know that an converges, and then bn would also converge.
Yep.
If it was between 0 and infinity.
Yep.
So it doesn't matter which one. Yeah. All right.
That's right. So what he's saying is just that if I say an is 1 over n squared, this converges, and I choose some other bn, right? And I do this. I calculate this limit, and I get 5 out of it. Then I know that that other thing converges as well, because this converges, so this other thing is also going to converge. Okay, so let's try it. I have an example here. So the example is the sum n equals 1 to infinity of 1 over root n plus 3. Okay, so yeah. So what do I think is going to happen here? What do I think is going to happen? So I have to kind of take a guess as to whether I think, you know, that I don't have to take a guess in this case. But let's just for the sake of it, let's take a guess of what if I think this is going to converge or diverge, right? So let's just say diverge. So I'm going to choose a bn that I know diverges, okay? That I know diverges. So one that I know diverges is 1 over root n. That diverges, right? Because it's a p series with a value of a half. So the reason I do that is that we'll get an answer out of it. So you'll see here that if I try this, if I do the limit now, so an is 1 over root n plus 3, bn is 1 over root n. So I take the limit as n goes to infinity. Oh, shouldn't it have been absolute value? No, I think I'm thinking of something else. Yeah, there's no absolute values here. No, we don't need absolute values. It's fine. So the limit as an. Okay, and so just to be clear, this is equivalent to the limit as n goes to infinity of an times 1 over bn, which is much more commonly how it's written. Right? Or, yeah, times 1 over bn. So I will do that. So an is 1 over root n plus 3, and times 1 over bn is times root n. Okay, so we want to take the limit as n goes to infinity of root n over root n plus 3. Right? This is going to be 1. I'm pretty sure. Yep, it's going to be 1. 1 is greater than 0, less than infinity. So since we know, whoop, I should answer the phone, shouldn't I? Oh, it's random number. I don't know who it is. So since we know,
Never answer random phone calls. You
I'm
know?
gonna just mute it.
Never answer random phone calls.
Yes, no, I'm not gonna answer. So since we got a real number greater than 0 here, we know that they both either converge or diverge. So this diverges, so an, so by the limit comparison test, an diverges. Because bn diverges, and we got case 1 out of here. If I chose, for example, to compare this to, let's just say, okay, so let me say root n. Let's just see what would happen if I chose to compare this to n squared, 1 over n squared, I mean. So that would be, say, this is just trying something. What if I tried to compare, so this was, an was 1 over square root n plus 3. What if I chose bn to be 1 over n squared? This converges, right? So let's calculate that limit. So just to be clear, this converges. We know the answer. This diverges. We know that that's the answer. So let's calculate the limit as n goes to infinity of 1 over root n plus 3 times n squared. Right? So I can calculate this as L n squared over root n plus 3, right? What's the highest power of n? We have n squared, so 1 over n squared times square root of 1 over n to the 4. Just to be clear, that's the same thing as n squared, right? 1 over n squared, I mean. So this is going to be 1 over, and this is going to be square root of 1 over n to the 3 plus 3 times this, no, that doesn't make sense, times the square root of 1 over n to the 4. And I take this limit. Yeah, okay, I take this limit as n goes to infinity, and I get 0 on the denominator. That's not good. Well, I mean, it's okay that it's not good because I purposefully chose something that I knew wouldn't work, first of all. I knew this wouldn't work.
That's correct then.
Yeah, so we get undefined, which is none of the parts of the limit comparison test. We know nothing if we get undefined, right? So it's okay. So all that means is that
don't we get infinity? If
Yeah.
0, it's approaching 0, which means the top is approaching, like it's being divided by something approaching 0. So it's infinity.
I think it's infinity. And
I
then it
guess
still
technically
works.
It is infinity.
Yeah.
But
It's still correct. Like if you get infinity, that's fine.
It's still correct because BN converges, which is not the case.
But you can't say
Well,
1 over
it is
0 is not infinity.
It's a limit. It's not. There's like a rule for like if there's no such thing as like you don't actually do 1 over 0. It's 1 over approaching 0.
Yeah, this is infinity. But notice from the right side. From the right side. Are we approaching from the right side? Yeah, why wouldn't we be approaching from the right side? Okay, so technically I guess you can say this is infinity. Yeah, this is true. This is true. So we're approaching 0 from the positive numbers. So we do get infinity. So if we get, let's see what happens if we get infinity. If we get infinity and bn diverges, then an diverges. But bn doesn't diverge, bn converges. So we still learn nothing. So I purposefully did this to see what would happen if we did something that wouldn't work. So again, I'm comparing it to something that does converge. I already know that an diverges. Right?
Wait, isn't that limit n approaches infinity? It's not approaching from the 0 on the right side though.
You're right. You're right. This is as n approaches infinity. This goes to 0 plus 3 times 0. This is evaluating our limit. But I'm using this fact to say that it equals infinity, that 1 over, because we're technically approaching from the positive side. We're technically approaching, we have no negative numbers here, right? We have no negative numbers here. So we are approaching from the positive side. So we can say this limit, sure. We can say that this limit is infinity, but we still get it undefined as our answer.
Okay.
In general, if you're getting 1 over 0, stop. Just stop. There's nothing else to do. But here we can go a little further, but we still get the same answer. Okay, so there's that one. Let's try another example. The sum n goes from 0 to infinity of 2 to the n plus 1 over 3 to the n plus 2. Okay, we need to find just another sequence. I guess what would you say? Why is there any logic to choosing any sequence? I mean, the logic is if you think something's going to converge or diverge, because then you choose something that matches it, because then your limit will work out. But why wouldn't I choose, okay, let's say I think this is going to converge. Why wouldn't I choose 1 over n squared? Oh, because nothing would cancel in the limit. The limit would be harder to calculate. Right? So I'm going to choose Bn equals 2 to the n over 3 to the n, which, just to be clear, is the same thing as 2 over 3 to the n. Because now when I calculate this limit, I'm going to do 2 to the n plus 1 over 3 to the n plus 2 times 3, well, I call it 3 to the n over 2 to the n. Is that what he did? Yep. So I can now do something, and that something is, how do you do this? What? Oh, okay. So how he does this, I wouldn't see to do this, but let's try it. Is you factor out a 2 to the n from this. You factor out a 2 to the n from that. So 2 to the n equals 1 plus, 2 to the n times 1 plus 1 over 2 to the n. And then from the bottom, you factor out a 3 to the n. So 3 to the n times 1 plus 2 over 3 to the n times 3 to the n over 2 to the n. Sorry, there's a limit in the front here. Limit. Those cancel. And so our limit is just equal to, I'll limit as of 1 plus 1 over 2 to the n over 1 plus 2 over 3 to the n. Yeah. This limit is 1. Which is greater than 0 and less than infinity. So since we have something that's between 0 and infinity, since we know that this converges, then therefore by the limit comparison test, an also converges.
Wait, the reason for that one is the ratio, right? The r.
Yes.
Just 2.
Yep.
Okay.
It's a geometric series with r, absolute value r, less than 1. Right. Absolute value of r less than 1. Okay. That's that example. Let's take a look at the next one that I have. I mean, of course, anybody can stop me if they have questions. Don't worry. Or if you want to just type in the chat, I have discussions open. Or if you want to private message me, you can private message me. Anything I am open to. Ln n over n. So sum n goes from 1 to infinity of ln n over n squared, actually. So we take, so to do this, we're going to compare it to, so an is ln n over n squared. What I want to choose is a sequence that I can compare it to that's going to cancel. Something's going to cancel nicely in our limit. So I'm going to choose bn equals 1 over n squared. Okay. So when I take this limit, so the limit is as n, sorry, limit of as n goes to infinity. I thought there was a problem with the recording for some reason. No, I think we're good. We're still recording. Yes, we are. Limit as n goes to infinity of, it's going to be, well, let's just try to say an over bn. So that's going to be limit an is ln n over n squared times n squared, which is just going to be the limit as n goes to infinity of ln n. Right? So the limit as n goes to infinity of ln n is just infinity, isn't it? Yes, it's just infinity. So we get infinity here. So what do we know about the test? Okay, what happens if we get infinity? If we get infinity and Bn diverges, An also diverges. So we get infinity, Bn converges. Inconclusive. Therefore, inconclusive.
Do we end there, or do we try to solve natural log of n over n squared with other?
What'd you say? What? Sorry? What?
I said, do we end there, or do we try to solve natural log of n over n squared with another test?
A different, yeah, we choose a different one.
Yeah,
we choose a
could
different
do
Bn.
that, right?
We choose a different Bn, yeah. So, he chooses, I really don't know why. I couldn't tell you why, but
Wait, and did you choose the 1 over n? Or did Horowitz choose that 1 over n for, like, illustrative purposes?
oh, he chose it. He chose it for 1 over. Just 1 over n squared. He
But,
chose
like,
it.
I was gonna say that it would be useless to choose 1 over n, but like you can just see from that it'd be less than ln n times n over 2. And since it converges, we know that it can't give us any information about the one that's
That's
under
true.
inspection.
That's true. That's true. Yeah. I don't know if that's always true, because yeah, I guess it would be. It would be true here. Yeah.
Direct comparison test.
Yeah. Yeah. Yeah.
That's what I was thinking. Like.
Yeah. You're right. You're right. Yeah. That would be true. Usually, you don't know for sure that something's always bigger than. You don't have to know that for the limit comparison test, that something's always bigger than another, right? Like bigger than an or smaller than an. So I didn't really think of that, but yeah, you're right. You can see just by here that since this is bigger than this, right? Then you won't learn anything. And Bn is convergent, then you don't learn anything about this. Yeah. Or Bn is Bn's convergent.
Yeah.
Yeah, but
So,
this is bigger. But this is bigger. So yeah, you don't learn anything. Yeah. Okay,
Wait.
so yeah.
What was that about with natural log of n squared? Natural log of n over n squared being bigger. Like, what does that have to do with the LCT?
Nothing. It doesn't have anything to do with limit comparison test. It has to do with the comparison test,
Okay, so.
right?
But would we just end there, or would we try something else?
No, we
to
try something
solve?
else. We try something else. We try a different
Okay,
Bn.
we can't answer n with inconclusive.
No.
I leave it from experience. Okay.
No,
Yeah.
yeah. So I really don't know why, but he chooses 1 over n root n, which is equivalent to 1 over n to the 3 halves.
Does that something to do with like I remember something like what's it? The L'Hopital rule or something like that. I remember my CP purposely choosing something that's smaller to still have something in the denominator when you're finished.
Sure. Yeah. That makes sense. That does make sense actually. To choose something that's
Yeah.
smaller, so you have something in the denominator, smaller than 2, because then you'll get.
But like still greater than 1, yeah.
Yeah, you want a value in the denominator after, right? Because
Yeah.
that'll make the limit as n goes to infinity not infinity. So, yeah.
I just want to say something regarding that.
Yes.
So Majid told us like a trick regarding like whenever we face such kind of case, and it was like, so you see for Bn the denominator that we chose was n squared, right?
Yeah.
Yeah, and so he told us to multiply like the 2 by 2 over 2, and then you subtract 1 from the numerator.
Multiply.
And
Yeah.
And he did this like to many examples, and it worked with him too. So he told us to use this method like whenever we face such kind of questions.
Okay. When you what kind of questions? Where it's just like you have a single something to the power of something in the denominator?
Exactly, and like when it doesn't work, like with in such kind of case, You just use this method in order to know
Okay.
like which bn to use.
So if you have something like the sum n goes from something to infinity of something over n to the c or n to the a,
Exactly.
then you choose your bn to be n to the, okay, I'll write it like this, n to the exponent, and the exponent is going to be a
Times 2 over 2.
a over 2 times 2 minus 1, like this,
Exactly.
like that, 2a minus 1 over 2. Okay, sounds like good advice to me. Yep, I'll even put that in my notes because that works for here, right?
So that's a formula. Okay, yeah, that makes sense.
So if you have something over n to the power of a, you choose your bn to be that. Plugging that into here, that will work. We'll get 3 over 2. So sure. I don't know why, but well, I guess I vaguely know why because it's going to help in when we do L'Hopital's rule in the limit. But
Yeah.
okay. So let's try it with this. So this is going to be. Let me see if I have it. Yeah, I do have it. I was gonna say where would it go? The limit as n goes to infinity of an is ln n over n squared times n to the 3/2. Okay. What we get is we get the limit as n goes to infinity of ln n over root n. I think that's right. That is. And from here, we can apply L'Hopital's rule. Technically, we have to make it a continuous function, but it's okay. So here we can apply L'Hopital's rule. So this is going to be 1 over x over 1 over 2 negative 1. No, not negative. Subtract 1 from the exponent. Yeah, not negative. 1 over 2 root x. So this limit in the front still. So this is going to be 1 over x times 2 over root x, limit again. Limit of, so 2 comes out to the front, limit of root x over x. So 1/2 minus 1 is negative 1/2. So this is 2 times the limit of 1 over root x. Remember the limit is, I switched it to continuous, but so limit as x goes to infinity, and I'll just switch it to discrete again. So 2 limit as n goes to infinity of 1 over root n is 0. Right? Hold on. Let me just make sure that's what I was supposed to get. Yes.
Yeah, because then converges both.
So we go back to our test. What happens when we get 0? If we get 0 and bn converges, then an also converges. So we got 0, bn converges, therefore, by the limit comparison test, an converges.
Beautiful stuff.
And there we go. So we have a nice formula there to help us out. That formula helped us out exactly for this question. So that's nice.
Which professor gave this? Which professor gave this? Was it Master?
I don't know. Maybe the person can
Can you scroll down to the
chime in.
last part of it?
It's Majid. Majid used it.
Yeah.
It was Magic that told us about it.
I see.
Yeah.
Okay.
Yeah.
Okay. So then let's move on. Let's take a look at the next one. We had this one, so this is the last one on my page here. This is going to be one with factorials. So factorials are always fun. Not very much actually, but it's okay. Sorry, did I just get something? Maybe a car just passed by. So this is going to be the limit, determine convergence, divergence for the sum n goes from 1 to infinity of 1 over n factorial. Okay. Before I look at the page, what would I choose to compare this to? That would be easy to figure out. I could say n plus 1 factorial. Nope. Okay. For some reason, he chooses 2 to the n. So an is 1 over...
What's my guess as to what 1 over n factorial would be? Divergent or convergent?
1 over n factorial, my guess is that it's convergent. And that is the answer. It is convergent. So we'd want...
because it's going down to 1, right?
Yeah.
Hypothetically.
So how do we... So b... Oh, sorry. This is not 2 to the n. 1 over 2 to the n. Sorry. 1 over 2 to the n. That also makes more sense. Since my guess is that this is convergent, I'm going to choose a convergent sequence, 1 over 2 to the n. Why that one in particular, I don't know, but that's okay. Let's just do it. So limit as n goes to infinity of 1 over n factorial times 2 to the n, which is 2 to the n over n factorial. Limit of that. Oh yeah, actually I vaguely remember this. This is what I have written on my page. Equals 0 by reasoning. So, essentially what I think this means is that, look at this for a second. Look at this fraction. On the top, I have 2 multiplied by itself n times, right? N times. There's n of them. On the bottom, I have n, I'll write it like this. N times n minus 1 times n minus 2, dot, 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 whoops, dot, 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 2 times 1. In both cases, we have n terms. Is that true? Hold on. Yes, in both cases we have n terms. On the top, all of them are equal to 2. On the bottom, most of them are greater than 2. So the limit as n goes to infinity, the denominator grows much faster. So it's 1 over infinity, which is 0. So I think that's the reasoning. Not very clear, but it is 0. So what happens after that? Well, we got 0 as our answer. So let's go to our limit comparison test. What do? We get 0. If we get 0 and bn converges, then an also converges. So bn converges. Therefore, by the limit comparison test, an converges. And there you go.
Why does BN converge?
Because it's a geometric, where am I? Geometric series. It's R value of a half. Okay. Okay, any questions about this one? Oh, sorry.
Can you just explain the two things actually? With the previous phone question, you were saying make continuous. I mean, just put in the realm of x, right?
Yeah.
That's not okay. Next.
L'Hopital's rule is
yeah,
continuous.
You can't use it. Yeah, and then for this one, it starts. It actually doesn't it end? Okay, like it can't be less than 2, because like you can't get 0. Like the factorial, like the smallest it can get is to 1, right?
Yeah, 1 factorial is 1.
Yeah. So I don't know. I guess. Nah, I don't know where I'm going with it. I can't put this.
Yeah, maybe you're thinking what if n equals 2, right? What if n equals 2? Then it would be 2 times 1, 2 over 4, which is not 0. But remember, we're taking the limit as n goes to infinity. So for any bigger number, the denominator is going to be much bigger than the top, right? So we just end up being, well, okay, even bigger than 2, 3 still, but the denominator is going to end up being much bigger than the top very quickly.
Oh, yeah, because it gradually increases like from 2, 3, 4, 5, and so on.
Yeah, right. If I go compare, what is it? 1 over x. 1 over x factorial. No. Compare x factorial and 1 over 2 to the x. Whoops. No, sorry. I meant to say 2 to the x. At first, 2 to the x is above, but then very quickly, x factorial goes above.
Yeah, this is like, I think after it passes 2, right?
After it passes 3.64.
Okay.
Right. And don't worry too much about how you can have 3.64 factorial.
No, I'm not worried.
You
I
can.
leave it at this.
You can, but yeah. Okay, so there you go.
Weird though, you can't use like decimals for factorial in the calculator.
You can't, well, because the factorial function is defined for integers, but this function is not the factorial function.
It works.
This is not the factorial function. This is called the gamma function. But that's not at all related. Well, I mean, it is related to calculus, but it isn't related to any of the content we're doing right now. So yeah, but
because it's actually 1 minus the variable to a factorial, something like that. Yeah.
Yeah, right. That you can expand the factorial like that. Yeah.
Okay,
so any more questions about this one?
How do you to the power of n?
Because I'm doing an. Sorry, how did I get to the power of n here or in the limit?
Oh, for b, yeah.
Why did I choose that? I don't really know why I chose that. I'm gonna be honest. I don't know why I chose
okay.
that.
Because the great God Horowitz.
Because Horowitz chose it when he did it. I don't know why that is the right answer, but I suppose because then this is true. Then you can do this reasoning. For that reason, but any number would work there.
Well, then can't you also choose 3 to the n?
Yes, that would.
But you just want to choose but you can also just want to choose like a reasonable number,
Yeah, something that looks right, I guess, but.
Mm-hmm. Something small
that you can work with. Yeah.
Yeah.
That doesn't take too much work.
Mm-hmm.
Okay, I'll go ahead and write the next example. The next one is the sum n equals 1 to infinity of n fourth root of n over the cube root of n to the 4 plus n squared. So, what are we going to compare this with? This one actually kind of makes sense to me why I'd compare it like this. What would make this a lot simpler? If I could do one thing to make this a lot simpler, what would it be? Well, I would get rid of this n squared. Right? Because, or the n to the 4, but let's just do the n squared. Because what we're going to end up with is it's going to be, so if I choose my bn to be the cube root of n, sorry, the fourth root of n, over the cube root of n to the 4, well, this is n to the 1/4, this is n to the 3/4, so 1/4 minus 3/4 is negative 2/4, so negative a half, so this is 1 over root n. Let me make sure that's right. No, what?
Wait, what are we solving for? Is this on the left side an, and we're trying to make a bn?
This is an. The thing we're given is an. Yeah, the thing we're given is an. Fourth root of n over cube root of n to the 4 plus n squared. Then bn is something simpler to work with, which I thought would be 1 over root. What? How is it not 1 over root n? Oh, because it's not what I just said. It's not. It was cube root of n to the 4, so that's 4 over 3. There you go. So that's n to the power 4 over 3, which is 1/4 minus 4 over 3 is 3/12 twelfths over 16 twelfths, so I get negative 13 twelfths. This is n to the power of negative 13 twelfths. Okay, that's okay. It's simpler. It's one thing now. So let's do the limit comparison test. Limit as n goes to infinity of, I'll do it all with exponents, n to the power of a quarter over n to the 4 plus n squared to the power of a third times n to the times n to the 13 over 12. Notice it's positive here now, not negative there, because I'm doing 1 over. Okay, well, let's do this limit. I'm going to add a quarter to it. So 13 over 12 plus 3 over 12 is 16
How
over...
come it is negative? How come it's positive now?
Because the actual formula that I'm doing is I'm doing the limit as n goes to infinity of an over bn, right? So
yeah,
the same thing as multiplying by the inverse. So 16 over 12 is 8 over 6, which is 4 over 3. Is that right? Did I do that right? 3/12 is a quarter. Yeah, 16 over 12. Looks right to me. So this is equivalent to n to the 4 thirds. Now we take the limit as n goes to infinity. Okay, so to do that, we take the highest power of x, which I guess will be n to the 4 thirds. Yep. And I divide both sides by n, top and bottom by n to the 4 thirds, n to the, well, this will be cube root of n to the 12 thirds. Yeah, because I multiply. So to do that, I say, well, I want to multiply in by, yeah, I want to multiply in to here, right? But that's inside of a cube root. So I have to have the cube root of something. So I want the cube root of n to the a to be equal to 1 over n to the 4 thirds, right? Because that's what I'm dividing top and bottom here, multiplying top and bottom here by. So, well, I can just solve for a here, honestly, and this works. So 1 over n to the 4 thirds. No, sorry, this is cube both sides. So it's going to be 12 thirds, and then, well, n to the a equals 1 over 12, 1 over n to the 12 thirds. So that's all I need, because this was n to the a. So I'm just going to put 1 over n to the 12 thirds. And there we go. So that's kind of the reasoning I did to find that 12 thirds. That's what goes in there. So now I can do that. So what I get is this is equal to the limit of 1 over, now, inside the cube root, that's going to be 4 minus 12 over 3. I'm just going to do that on a calculator. Why do it by hand? 4 minus 12 over 3, which is, 0. What? 12 over 3 is, 12 over 3 is 4. Sorry. Yes, of course. 12 over 3 is 4. So, yes, we get 1. So, cube root of 1 plus 1 over n squared. And now we can evaluate this limit. This is equal to 1. So we got a finite number. So since the bn, we don't know anything about the bn. Hold on.
Are you sure? Isn't that just 1 to the n and then a little bit over?
Oh, you're right.
Greater than 1?
1 over, yes, n to the 13 over 12. That converges.
So,
so since I got a finite number greater than 0, therefore by the limit comparison test, an converges. Okay.
Yeah. Question: that part where you changed it to n 4 over 3 to the cube root of this new thing is just so that you can divide the denominator properly, since
Yeah.
it's already.
Since it's in a cube root.
Yeah. Cool. So you just it's the same value. You just changed it so that you can divide through.
Exactly. I want it to be equal. Yeah.
Do we have to show that work, or could we just get rid of n to the power 2 in the denominator?
Oh, you probably have to show at least that you're multiplying top and bottom by something like this. You probably don't have to. You don't have to show this, but in the green box, you don't have to show that. Although it might be useful. And then, yeah, you probably should show that you're multiplying top and bottom by something. So yeah.
One.
What'd you say?
No, we got root. Sorry, how did it go from cube root to the square root?
Where's the square root? Oh, you're right.
Square
You're
root
right.
one.
This should be cube root.
That should be cube root. Okay. Yeah. Okay.
Yeah.
Yeah.
That
That
should
makes sense.
Okay. We're good. So let's look at the next example that I have. The next example kind of just, I'm going to be honest, it just kind of looks like an annoying question. I guess that means let's do it, but let me just look at it for a second.
Yeah. Honestly, are you still gonna go till 9?
Yeah.
Okay. I don't know. I think for some people, being burnt out, because I'm kind of burnt out.
Yeah.
Well,
Yeah. No, I
tomorrow
understand.
as well,
I understand for
because-
sure. This has been a while.
Yeah.
Maybe we can take a 5-minute break. Everybody can take. I could get a snack. Let's take a 5-minute break, everybody, and then.
I got a question.
Yeah, for sure.
When you come back after 5 minutes, can you go over this one more time? Because I kind of got confused halfway through.
Sure. Okay. Yeah, I can do it now. I can do it. That's okay. So, let's do it now. So, so we start with this, right? I need something to compare it to that's simpler to deal with, and that I can preferably know quickly if it converges or diverges. Right. That's what I need. So what I'm going to do is I'm going to just knock this guy off. Okay. I'm going to knock off that n squared. And so what I get for my bn is that, just with the n squared gone. I simplify it and it turns into this. And I know that converges because it's a p-series greater than 1. Okay. So now I do the limit comparison test. I do an times 1 over bn. It's this. Right? Oh, sorry. Sorry. I made a mistake there. This an is kind of not written properly, so I should actually write another line here. Technically, we start with this. An, which was n to the 1/4 over n to the 4 plus n squared to the 1/3 times n to the 13 over 12. That's our first line. That's our second line. It simplifies to this. Then I decide, okay, so to evaluate limits like this, you need to multiply top and bottom of the fraction by 1 over the n to the highest power of n. So the highest power of n that we have here is 4 over 3. So I multiply top and bottom by 1 over n to the power of 4 over 3. What that does is that on the top, I get a 1. Okay, on the bottom, it's a little more complicated. On the bottom, it's in a cube root. Right, it's in a cube root. So I need the thing that I'm multiplying to also be in a cube root. So essentially, I want the cube root of something to be equal to 1 over n to the power of 4 over 3. Because remember, that's what I have to be multiplying by on the bottom. 1 over n to the power of 4 over 3. So I want the cube root of something to be equal to that. So just cube both sides, and I get n to the power of a. So the cube root of n to the power of a is equal to 1 over n to the power of 4 over 3. What's n to the power of a? N to the 4. So this is n to the 4. 1 over n to the 4. So I multiply the bottom by the cube root of 1 over n to the 4. To be clear, that's equivalent to this. I just showed that here, right? It's equivalent to this. So on the bottom, I get the cube root of, now the the reason this has to be cube root is because this value has to go in the cube root. So essentially I'm dividing by n to the 4 on both of these, n to the 4. So I get 1 plus 1 over n squared. The cube root of that, plus 1 over n squared, right? And the limit as n goes to infinity of that is 1. So then since the limit is finite and less than and greater than 0, then since this guy converges, our Bn, by the limit comparison test, An also converges.
Thank you. That makes so much more sense.
Okay, good. Sounds good. Okay, let's take 5 minutes. I'll go get some water and just snack, and then I'll be back in 5 minutes. So, good to take a break. Let's say AFK. I know we're almost at the end, but still, it's good to take a break. So, back at 8:36 p.m. Okay, so back in a minute. Okay, guys, I am back. Hello, hello. Let's get back into it. So, is everybody ready to keep going? Just for another about 25 minutes. Okay, I take that as a resounding yes. Let's start the next one. Is there any questions for these ones that I started with? I mean, the ones that I did just now? Okay.
8 times 8, 2 minus 1 over 2.
Could you say that again? What you cut out there a little bit? What? Hello, hello.
Yeah. Can you hear me?
Oh, now I can hear you.
Yeah, I was just wondering about the question with the thing that he gave from Masjid with the, what was it for? For only ln functions?
No, if you just have something over n to the a.
Okay. All
You
right, cool.
choose your bn to be that.
So then our BN would be that. All right. Cool. Thanks.
So I'm gonna write that down. I'm gonna definitely add that to my notes. Let me see here. What is
It's
this?
pretty good.
Yeah. I'll just say add something over n to the a formula. And also add just the other notes. And just something else to add. What did you say, sorry?
That's sort of like a hard point. I was just curious.
Oh, this is just a pencil. That's all it was. That's it.
Dude, you write so hard.
Yeah, I guess I was just writing a little hard there. Yeah. One thing I actually just realized that I didn't mention, for 5.3, there was something that came in useful a few times for me, and it's this. Oh, I don't have it written anymore. Okay, but it's this. Let me see if I can find it again. Let me see if it's here. Yes, it's this. Can I get that? Yes, it's this. So, don't do that. No, don't do that. It's selecting everything. I don't like that. Okay. This came in useful a few times, so I'll just write it here. Comes in useful when you're rearranging. So, there you go. You can prove it's true. I mean, I can probably prove it's true, but...
Use this?
I used this for 3 of the homework problems. Or was it 2 or 3? I forget. I forget if I used it for the 3rd one. But I definitely used it for 2. So, yeah. I guess we're just supposed to know this. I don't know. Or just figure it out ourselves. I'm not really sure. But, okay. Anyways, let's see this next part down here. Just to be clear, that's for 2 or 3 of the homework problems from 5.3, not 5.4. Okay, so let's try the next one. This next one that I have seems like it's very hard for no real reason. So e to the 1.01n minus 3 to the n is our series. And of course, n goes from 1 to infinity of 1 over e to the 1.01n minus 3 to the n. Okay, so what do we compare this to? What does he compare it to? I'm going to start with that. Wow, okay.
Still use the trick, or does it not work since it's no longer just n? Oh wait, that was n to a number. Never mind.
Yeah, it was just n to some power.
Yeah.
Okay, so this is a hard question because you have to do. Okay, so let's see what's happening first of all.
Could you go up for 1 second?
Yes, I can.
I just missed
Here, or
it. It was that formula for if you have something over n to the.
this one here.
Okay,
Right.
thanks.
There. Good. Okay. So, okay, the thing you have to recognize with this is that e to the 1.01 is greater than, no. What? Yeah, is less than 3. So what we're going to get is this is a negative series for all n. This is negative. Right, so an is less than 0 for all n. Again, that just means negative. So that means we cannot do the limit comparison test. We can also not do the integral test. But it doesn't matter. So no limit comparison test, no integral test. So what do we do? So what he does is this. Take the negative of this. Okay, so the negative of this is n equals 1 to infinity of 1 over 3 to the n minus e to the 1.01n. Now this is positive. Just to be clear, it was negative before because this is small. E to the 1.01 is smaller than 3. So this bottom will always be a negative number. So, and the top will always be positive, so it's just like that. Okay, we factored out a negative there from the bottom. And now, since this is positive, we can just choose some bn. So I will choose bn to be 3 to the 1 over 3 to the n. Yeah, 1 over 3 to the n. And we can just do the limit comparison test with this. Well, when I get to it, when we get to later on, we'll see why this makes sense. So hold your horses for a second. So let's do the limit comparison test, see what we get. So the limit as n goes to infinity of 1 over 3 to the n minus e to the 1.01n times 3 to the n. Okay, I'm going to factor out a 3 to the n from the bottom here. Pretty sure that's what he does. Let's see. That is what he does, yep. So I'm going to factor out a 3 to the n from the bottom. So it's going to be the limit of 3 to the n over 3 to the n times 1 minus e to the 1.01 n over 3 to the n. Those cancel, of course. So we have 1 over 1 minus e to the 1, I'll even write it like this, e to the 1.01 over 3 to the n. Okay, the limit as this goes to infinity is 1 minus infinity is infinity, so this is just 0. Nope, this is 1, sorry, because this goes, wait, what? No, that doesn't make sense. How is that? 1.
Is that e to the 1.01 over 3?
Yeah.
Okay.
Zoom in and write this. E to the 1.01 over 3 to the n.
Yeah, okay.
Right? Oh my god, sent me way back up.
Let's see how that looks. Oh, cool.
So, somehow that's 1. How's that 1?
Isn't the...
Didn't we say that 3 to the n was greater than e to the 1.01 n?
Yeah. Oh, okay. Yes. Okay. So then this is yeah. Okay. It's exponential decay. Yeah. Okay. This value e to the 1.01 is, so e to the 1.01 over 3 is 0.915. 0.915.
Close to 1.
Yeah, but it's less than 1 though. So that to the power of infinity is 0. You can see this by saying 0.9, what was it? 152 to the power x. And you see where as n goes to infinity, as x goes to infinity, the height approaches 0. If you're between 0 and 1, then you have exponential decay. So we lose.
1.
Right?
Okay.
If the base is between 0 and 1.
Sorry, base.
Yeah, so the base of the
okay.
exponential function, the base of the exponential function, if that's between 0 and 1, then you have exponential decay. So that goes to 0, so this is 1. Sorry. Okay, I don't know why I was so confused by that. That makes sense. So we get a finite value. So since we get a finite value, we know that this converges. We know that this converges, right? Therefore, we know that the sum n goes from 0 to infinity of 1 over 3 to the n minus e to the 1.01 n converges. Okay. 3 to the n minus, yep. And since our value, which is the sum n equals from n equals 0 to infinity of 1 over e to the 1.01 n minus 3 to the n is equal to negative the sum n equals 0 to 1 to infinity of 1 over 3 to the n minus e to the 1.01 n. Since this converges, this converges. Not by any test, by the equal sign that is between them. I didn't hear what you said. That you cut out. Could you say that again? Sorry.
Just consistent, because I was gonna say, isn't the original function the opposite, like the negative? So we can just equate both of them converging to each other.
Yeah. Since the right side is convergent, they're equal, so the left side must be convergent. And that's that. Okay, it looks like I have... Yeah, sorry. Go for it.
The original question was 1 over 3n, or was it the other one? Wasn't it?
This was the original one. This is the original. So I'll say therefore converges. That's what we're looking for. Is this one.
Okay, I live with it.
Okay, I got 2 more from Horwitz. Any more questions about this one though?
Wait, isn't it?
Sorry, I think there was 2 people talking there, and I couldn't hear either of them.
Jeevan, go ahead.
Yes, scroll for a second. Yeah.
Yep. Perfect. Okay, thanks.
Good. Okay, no problem. And
Alright, can you explain like what you did in this in the first step to get that negative for it?
Well, yeah, I factored out a negative from here, right? I divided both by -1, so it's going to be positive 3 minus that, which is equivalent to what I wrote here, right? So I just factored out the negative, and then remember you can factor out a constant multiple outside of a sum. So I just did that. So I'll just put that.
So would it be like a -1 at the end, because like it converges to a -1?
Where, like up here?
Oh, because at the end you got a 1. So I mean that sum converges to a -1.
This sum converges to 1. This isn't a sum.
So,
this isn't a sum.
Okay. Okay.
This also, just to be clear, this doesn't converge to 1. The limit comparison test, the limit comparison test gets 1 as a value.
Converges to 1.
Right. But we don't know what value these things converge to. That's a whole different ballpark. Right? We're just asking if they converge or not. Yeah.
All right.
So yeah. Okay. There you go. So second to last one that I have. So 1 minus cos 1 over n. Sum from n goes from 0 to infinity of 1 minus cos 1 over n. Okay, so we're doing the limit comparison test. So an is 1 minus cos 1 over n. What's something that we can compare this to that would be possibly useful, that we know convergence or divergence of? Again, for reasons that I don't really understand, let's see if we can figure it out. He chooses 1 over n squared. So I see that you would want to have... You would want to be able to take... Yeah, okay, let's just do it and let's figure out... Maybe let's see if we can find a reason why after. So limit as n goes to infinity of 1 minus cosine 1 over n times n squared, essentially. Wait, what? How did he get... Oh, okay. Times n squared, which is equivalent to over 1 over n squared. Okay, so that's how he wrote it. So to evaluate this limit, we... well, of course that's equivalent because that's what we're doing. an over bn. Right? So we have... to take this limit, well, I can do L'Hopital's rule. So L'Hopital's rule says this is going to be sine 1 over n ln n? What? Oh, no. Okay, he does something much more complicated. I see. Okay. So, to do this... Yeah, okay, I see what he does. So sometimes you can do a variable change, which I've seen Horowitz do a few times. You can do a variable change. sometimes it's useful when you're evaluating a limit like this because you have a 1 over n in two different places. So if I just define x to be 1 over n, right? Then let's think about it for a second. What happens as... So first of all, I can say limit. I'm not going to put the thing under the limit for just now. It's going to be 1 minus cos x over x squared. But now what's our limit? So as n goes to infinity, x goes to 0. So as x goes to 0, going to just check that that's right. Yes. And from the right, to be clear. I guess that's a distinction that has to be made. I don't really know exactly why, but it is a distinction that has to be made. You're going, so remember, as n goes to infinity, as n goes to infinity, this approaches 0 from the right. Yeah, it's just, sure. Or from the positive side, I should say.
Do we do that because n can't be negative? Like, it's a series, so you can't...
Yeah, you're dividing by positive numbers, so it's, yeah. Although I don't think it really matters here. Let's just see if it matters, but I don't think it matters. You could just leave off the positive. It approaches 0 as n goes to infinity, so no matter what, actually, I would even leave it off. Let's see if it comes in handy, but I'll leave it off to avoid confusion. So now I can evaluate this limit using L'Hopital's rule. So this is going to be now sine x over 2x, right? And as the limit as n goes to 0, as x goes to 0, from the right. So we do have to choose from the right. 0. Oh, I think you do L'Hopital's rule again. And this is going to be cos x over 2. And now you can apply the limit. I should be clear, there's a limit on all these things. So the limit as x goes to 0, so cosine of 0 is 1 over 2, which is bigger than 0, less than infinity. So, since I got that, my Bn is convergent, so my An is convergent. Therefore, by the limit comparison test, An is convergent.
You could probably also solve that with an identity, because you have 1/2 times sine x over x, and the limit of sine x over x is like one of those identity ones.
That's true. Is equal to 1. Yep.
So then it's 1/2 times 1.
That's true.
Yep. See that second line where you have limit as n approaches infinity, and then you have the actual question. Well, an over bn. You just switched it into a continuous function and then just solved.
Well, I didn't just switch it to continuous function. I did this substitution. I said x is equal to 1 over n.
Oh yeah, instead of just like switching x to n, you actually made it.
You actually have to make it 1 over n, because then this goes an x in here, and this goes an x down here, or x squared down there. But then I also have to adjust the limit. I have to change the limit. So now it says x goes to 0, because you just apply the limit to this. And where does x go when you apply the limit to this? Well, it goes to 0. So x goes to 0.
Makes sense.
And again, from the right didn't matter. Yeah?
I think because n goes to infinity, and I think n starts, it doesn't go from, it doesn't start from like less than 0.
No, it's a positive. Yeah, exactly. Yeah, but so it didn't actually matter. It didn't actually matter that we called it positive 0 from the right. So it didn't matter. It didn't change anything. But it's okay. Whatever.
Yeah. All right.
So this is the limit as n goes to infinity of an over bn. Way too many colors, but I'll just. Oh.
I'm colorblind, so I only see black.
Yeah.
And white.
Okay, well, you're living in the 50s, I guess. There you go. That's good. Yeah.
You know, actually, yeah.
Yeah.
I used to believe that was the case.
Yeah.
Crazy.
Yeah.
Yeah.
Okay, let's take a look here at this last one. This is. Oh, this is kind of a. I'm gonna be honest. This is a complicated one.
We can end the. We always ended on a very bad question.
Yeah. Well, how about I'll write it. I'll write it, and we'll see what we decide. So for what values of p does the sum n equals 2 to infinity of 1 over ln n to the p converge. This is essentially kind of a power series.
I swear this was the question, one of the questions on the quiz this week.
Well, yeah, but it was like p minus something. But I think for this one, it's just gonna be greater than 2. Something like that. Because I remember in the Paperlight quiz, it was like p minus 6. And then at first, I did the first option and I did greater than or equal to 7. But then you can't use 7 because it's going to be ln of n. And then that's not. You can't use that.
I actually don't have the answer for this one, so let me find it in Horowitz. I think I didn't write it down.
If you think about it, right? When we put ln n to an exponent of something, that means we're Sorry, no, I'm thinking of log rules, but I'm thinking it inversely. Never mind. So I'm thinking ln n times ln n would equal ln n plus n, but that doesn't work. It's
No.
in the inside.
No,
It's on the inside.
but we did prove ln n of n earlier today, and so it applies here. So p can't be equal to. I don't know. Would it just be greater than?
First glance, I know you can turn ln n into e to. Wait, no. Is it e to the ln of ln n?
Just e to the ln n is. Oh no, sorry. E to the ln of ln n. Yeah.
Yeah, and then you could technically move the p into that exponent, but I don't know what that would.
Oh, yeah, you can move the p down then.
Well, what would that do? Like, how would that help though? Like, because I've seen it before, but wasn't it?
I'm trying to turn it into like a something to the power of something rather than like a ln function.
Yeah.
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 So
it's just weird that we're using p.
I can show. I'll go through how Horowitz did it. Okay, so what he does is he compares it to 1 over n.
Figured.
No, that's not true. He compares it to 1 over n to the p.
What?
He compares it to 1 over the n to
Oh
the
yeah,
p.
yeah. But then p would still be greater than 1.
I would think of that too.
It goes 1 over n to the p. So let's do the limit comparison test. Limit as n goes to
H right there.
Of that's a solid what?
That's a solid h to the p right there. I don't see anything.
Whatever. I'm just leaving it. 1 over.
Hey man, don't attack me.
Yeah. N to the p over ln n to the p. Okay.
Yeah.
So we can do L'Hopital's rule on this, I think.
Wait, why? Because it's infinity over infinity?
Oh, hold on. Oh yeah, no, we don't need. Yeah, never mind. We can't do L'Hopital's rule on it anyways. So what he does? Whoa, why did he do that? What?
His orbits.
If it made sense, it wouldn't make sense.
Yeah.
That's a paradox right there.
Yeah.
It's Horowitz. If it made sense, it doesn't make sense.
So, okay, so some.
This is the Horowitz moment right here. Just saying.
Yeah. Okay. So I can of course do this. Ln n to the p. I can take the limit inside. N over ln n to the p. I can do L'Hopital's rule, 1 over n to the p. And then I get infinity to the p. I get infinity, no matter what. So it equals infinity.
You got?
But hold on, infinity. What is this? Hold on. And okay, so the answer is infinity, but the answer that's written is p less than or equal to 1. Oh yeah. Because if I go to, so I got infinity from I got infinity from my thing. So an diverges if bn diverges. So an will diverge.
Yo, that makes sense though.
AN will diverge if BN also diverges. When does BN diverge? If P is less than or equal to 1. For
It's
P...
basically the same thing from the bit polite.
But this is not the end. This is not the
The
end.
only thing we're
We have not
the only thing
found...
that's different.
Yeah, go for it. Go
I
for it,
was saying in the bit polite quiz, the only thing that was different is that P equal to 1 is wrong. Like, whichever value you do in the bit polite quiz, let's say like you have P minus 6, and you choose, let's say the value is 5. If you choose equal to or less greater than or equal to 5, it's not. It's just greater than 5. Because if you use 5, then you're gonna have ln to the negative. So that's gonna put it in the denominator. It's gonna be ln of n, which is divergent. So that's wrong.
Infinity. Yeah, exactly. So for this next part, what he does is he chooses specifically when P equals 1. So the harmonic series. And we do the limit comparison test, right? So limit as n goes to infinity of n over ln n to the p. He does L times, I'll do a few steps in one, L times the pth root of n, ln n to the power of p. Okay. Then he does L'Hopital's rule. So this is 1 over p times n to the minus 1 over p over 1 over n. Limit, of course. Limit n to the power of p. We now... What do we do? 1 over n. Yeah, okay. We now add 1 to the exponent. Somehow he just loses. Oh, sorry. This is sorry. This is 1 over p minus 1, which can turn into L, the limit of 1 over p n to the 1 over p to the p. Okay, this is limit as n goes to infinity. The limit as n goes to infinity of this is infinity to the power p, which is just infinity. So since we get infinity, and bn diverges, an also diverges. We get the
n.
On the bottom.
Yeah.
This
with the negative
and
one?
This cancels.
Okay.
Right. So
yeah, that makes sense. Yeah.
Since bn, that's okay. Don't worry. Since bn diverges, then an also diverges.
Yeah.
And so,
it proves each other.
So then an. So I'll write it like this: the sum an n goes from 0 to infinity, diverges for all p, and that's the answer. I don't know what the point of the first bit was.
We won't get that. I know we won't.
Yeah,
he would never give us a question. I know he would never give us a question he actually did. He's not that.
Oh yeah, he wouldn't give us exactly this question. No. But something of equal.
Can you scroll to see the question? Oh, a little higher.
A little higher? This is the question here, though. This is the...
Yeah, no, it's asking for conversion, or...
Which one, sorry? What are you saying, sorry?
No, is it asking when P converges?
Yeah, when does P... when does the sum converge? For what values of P does the sum converge?
And then we did the opposite. So, like, don't worry. Like,
we found that it
doesn't converge at all.
It diverges for all P, so that's the answer.
I know why. I feel like the only way, I think there's a question on OpenStax that was like ln of n squared, and like the power of n in the bracket has to be greater than the power of ln to be like not diverge. But if it's like all to the same power, you can basically take it as just ln of n, so that will always be divergent. If that makes sense.
Yeah.
So like
Okay.
if it's 1 over n of n, and it's all risen to the same power, then you could just consider it always
Ln
ln of n.
Yeah.
Yeah. So it's always divergent.
Could you prove that this diverges just by doing a comparison test? Could you say that 1 over n is would it be, I guess, smaller? Could it be smaller than 1 over ln n because ln n is logarithmic, and 1 over n wouldn't be? 1 over n would be larger than 1 over ln n. You could just say. Okay.
Yeah, 1 over ln n is larger than 1 over n. Yeah, so 1 over ln n to the p is larger than 1 over n to the p. And then we
I guess. So that means 1 over ln n would be greater than 1 over n.
We would get the same result as this first section. We'd get the same result as this first section.
Yeah, because you still have p, and then like p.
Because you have to know for what values of p. We don't want to specify p equals 1.
So you could, I guess, if you wanted to fast track this, you'd do the comparison test, then you'd have to check if p is equal to 1. Like you actually have to check if p was equal to 1.
I guess so.
I don't know.
Yeah. That's what we did. So I guess you have to check that. And then we discovered that it diverges for all p. So
yeah,
that would have worked to begin with. So I don't really know. This seems like the answer to me. This bottom part. I don't really like the top. Maybe is just like what you would do first. But yeah, I don't know. Anyways, that's all of Horowitz's questions. We did all of them. So that's good.
See you guys. Thanks, Adam. I actually have to finish another.
Okay. Yes, for sure. But have a good luck tomorrow. Have a good night. Everybody who's doing the ECN thing tomorrow, good luck. I'm doing as well. I'm probably gonna do some practice during the day sometime. So maybe just watch tutor announcements. I'll just post when I'm gonna do some practice. Not really planned that much, but just got work to do.
Yeah. Well, bye everyone. Thanks again, Adam.
Yeah, no problem. Have a good night. Good luck tomorrow.
Yeah. Thanks. You too.
Okay. Bye everybody. Or if I'm here for any more questions too. But yeah, bye everybody who's leaving.
Did I leave? I'm not sure.
No, you're still here. No problem though. Yeah.
Guys.
Bye, Joshua. Bye.
Adam.
No problem. Okay, any last questions from the three of you or Vikram?
Thank you so much and have a great night.
No problem. No problem. Yes. Good luck. Have a good night. Hope all was good.
Wait, Adam, quick question.
Yeah.
Are you going to be doing a chapter 5 thing for ECN?
Yes. I still have not touched it.
Okay.
You haven't either? What'd you say?
I haven't either.
You haven't either? Yeah, okay. So I'll do it tomorrow sometime. I'm not really sure, but I'll definitely let you know. I'll put it in tutor announcements too, but I'll also just message you when I'm doing it so you know. Okay, and we can work.
Okay.
Okay.
Awesome.
Sounds good.
Great.
Okay.
See you then, man.
Yeah, talk to you tomorrow.
Later.
Have a good night. And Maya, do you have any last questions? I can't. Your bubble's green as if you're talking, but I cannot hear you. And you're unmuted as if you're talking, but I cannot hear you. You can type in the chat too, if you want. You can also just DM me. I'll answer by DM. Hi, Fawn.
Hi, sorry I'm late. Are we
Can
still?
you hear me now?
Oh, yes, I can hear you now, Maya. Yeah.
Okay, I don't know what's going on.
That's okay.
I just had a question about the example after the one with the factorial.
Okay. This one.
Yeah, so it's just the algebra with the like what you did in the green box.
Yeah.
And then like just at the line above it. I just didn't follow.
So essentially what I have is this. I'm trying to evaluate this limit. I'll do it at the end here. I'm trying to evaluate this limit, right? So to evaluate this limit, what I need to do, if you ever any kind of like algebraic limit like this, which is like all just powers of the thing you're taking the limit of, right? What you do is you multiply the top and bottom of this fraction by 1 over n to the power of the highest power that you have here. So the highest power we have is 4 over 3, n to the 4 over 3. So we multiply the top and bottom, n to the 4 over 3, 1 over n to the 4 over 3. The reason we do this, okay, so first of all, we're allowed to do this because this is just 1. We're multiplying by 1.
Isn't that a complex fraction?
It's, yeah, I mean, it is, I don't know, like, by definition of what a complex fraction is, I'm not sure, but it is complicated, that's for sure. So, yeah, but we're allowed to do this because we're multiplying by 1, so that's okay. And the reason this is useful is because, look, on the top, this is just 1, right? This is just going to become, so limit n to the 4 over 3 over n to the 4 over 3, that's 1. And on the bottom, okay, on the bottom we have something a little bit more complicated. We have 1 over n to the 4 over 3 times n to the 4 plus n cubed to the 1/3. What we want to do is we want to write this. We want to write this 1 over n to the 4 over 3. Sorry, n to the 4 over 3 as something called a to the power of a third. Because if it's to the power of a third, then we can combine it inside this fraction with these guys here. Right?
Oh, okay.
So solve for a here. We can just solve for a, cube both sides, and it would be 1 over, whoops, be 1 over n to the 4 equals a. Does that make sense?
And then, okay, so then 1 over n to the 4 goes into the brackets in the denominator?
Yeah, because it's the cube root of 1 over n to the 4 times the cube root of n to the 4 plus n cubed. And now that they're both cube roots, they can go in. Sorry, this should be equals L. L is just the limit, right? And then, yeah, it goes inside. So it's going to be the cube root of n to the 4 over n to the 4 plus n cubed over n to the 4.
Okay, yeah, now I see.
Right? And this is just going to be 1 over the cube root of 1 plus 1 over n. And the limit as n goes to infinity is 1.
Yeah, I have little brain energy.
Don't worry. This is a complicated limit. It's a complicated limit. It is. So it's hard to do. But yeah, good to practice. Good to practice this kind of stuff. Yeah. Okay.
Thank you.
Okay, no problem. Have a good night. Good luck with everything. Or if you have more questions. Okay.
Yeah.
She's gone. There you go.
So I'm
How's it going?
late.
Yeah. Yeah, just a little. About 3 hours and 15 minutes late. Yeah. I guess so.
Yeah, so let's catch up on the convergence.
How about I teach you all of Calc 2 in the meantime? Yeah.
Okay, yeah, so wait, one thing I wanted to tell you,
Yeah.
I was recently looking at the prices for the RTX 3070. Apparently it's gone up by like, I think $100 nearly. Well,
Yeah.
it was 879, now it's a 950. So I was thinking, the difference between it and the RTX 3080 is like $100. So do you think it's just worth it at this point to just pay the $100 extra and get the RTX 3080? Yeah.
It's a big, expensive graphics card, but...
Well, the thing is,
yeah.
the 3070 is $950 without tax.
Yeah. It's still, it's already expensive. So, yeah.
And the 3080 is $1,159. So I
Let's,
don't know. I feel like it's. Yeah, sorry. Go ahead.
Let's see. GPU user benchmark. I can't spell, but GPU user benchmark, and then compare. And I want to say.
No, the difference isn't like too big, but I mean, I'm solely basing. How do I say this? What do you call it?
There's your
I'm
comparison.
basing my reasoning solely off of the price, not the performance.
Well, if it's just off the price, then go for the cheaper one. There you go. Simple. 3070. Right?
Yeah, I know that, but like, look.
Wait, I'm gonna ask you something.
Yeah.
It's like, are you like one of those people that stresses over performance, or are you the one who's just because like as long as it's like fairly smooth, like I don't mind. Like, what would you consider?
I mean, either way, 3070, 3080, you're gonna be great. Both are very good graphics cards.
No, I'm not debating on that. I'm just saying like.
Do you want maximum frames?
Yeah, like do you want maximum frames? Like do you want to like push the limit in some sense? Like if you just
yeah,
want to super.
My entire build is overkill, so.
It is pretty
How
over.
much?
Yeah.
How much is it if you don't mind telling me?
I think it's like $2,500 or more.
2,500.
I'm not paying.
Money.
No. But
Irwin's
the thing
just
you
brain
don't
just
understand-
exploded.
Bro,
The
that's
thing-
like a quarter of my tuition right there.
No, but the thing you're not understanding is I'm not paying for it all myself.
Ah, okay, that's good.
Yeah.
No, but okay.
If I was paying for it all myself, then yeah, that would be stupid. But like, if you're splitting it between 3 people, then
Yeah,
you
someone
know,
that people to help you. Yeah.
Okay, so how I'm taking it is if you just wanna like, if you're just like whatever, as long as it's like fairly smooth, like mine, then like buy the cheaper one. But if you kind of
Okay.
want to squeeze like max performance in your regular